correctly, Kaposi Ambrosch. So that it's on the internal parametricity without an interval. Please.
Yeah, thank you. So this is joint work with Torsten from Nottingham, Jorgo Shamoun, he was a student intern from École Polytechnique, and Mike Schulman from San Diego. And this talk will be about identity type in type theory, and we will get to parametricity very soon. So identity type or equality type can be used to express the equality of two different things. So for example, equality of 1 plus 1 and 2. So how do you prove this in type theory? This is the identity type here on the right-hand side, and the left-hand side we want to write a term. Oh, sorry. The connection is... maybe it's frozen, so replug and unplug, no?
That screen is frozen for some reason.
Yeah, that is frozen, but here it's fine. Shall I try unplug, replug? So it's some sense of fakeness. Yeah.
Yeah, in the meantime, we can kind of get people more in the middle for the red speech, because we're trying to fill up. So we're all friends here. Sit next to each other.
Yep. Yeah, okay.
Yeah, I should be looking up. Yep. Okay.
Right. Can I continue or restart? Yeah, so this is the identity type, which expresses equality of the two natural numbers. Here it's natural numbers of 1 plus 1 and 2. So, and on the left-hand side of the column, I need to write a term or a proof of this fact. So how do I prove this? Plus is a function which computes. We are in type theory, or a computer program which computes to 2. So in fact, I only need to give a term of type ID 2. And if I know that my identity type is reflexive, so I have this reflexivity term at 2 will prove for me that 1 plus 1 is equal to 2. Okay, so how do I prove something more complicated? I have a variable x, and now I need to prove that x plus 0 is equal to x. So here, this doesn't compute because I happen to define addition by recursion on the first argument. So it's piano natural numbers. So I know that if I add 0 to a number, it stays the same. And in the successor case, there's a recursion happening, but if the variable here is the first argument, then it doesn't reduce, so this is a Stokes term, so then I need to use induction or something more fancy to prove this theorem. And in general, so the identity type for every type A, I have the identity type A, which is a double-indexed family of types over ID of A, so you can take, this is like in the classical way of representing, it's a homogeneous binary relation, and we represent it with this characteristic function here. And if I have a term of type A, I also know that this type, I have reflexivity of A, which is a witness of the identity type, and then I have some more rules. So what are these more rules? How do I specify the other rules of type theory? So the way by Per-Martin-Löf is very simple, it's a very nice way. It's saying that it's an inductive type generated by the reflexivity constructor, and then this gives a notion of eliminator, which is the J. So one problem with this is that this only works well for identity of inductive types and not for co-inductive ones. So in particular, for function space, we cannot prove this in Martin-Löf type theory, that these two functions, x plus 0, which add 0 to an input natural number, or just the identity function are equal, so we need function extensionality or some extra principle, or a different definition of identity type, such as the one in cubical type theory, where there's a formal interval added to the syntax. This I is the formal interval, which has two formal endpoints, 0 and 1. And then you can say that two elements A and B are identical or equal if there's a map from the interval to A, okay, such that that map starts at, when it starts at its starting point, it maps the starting point 0 to A, and it maps the ending point, the endpoint 1 to B. And with this, you can actually prove the previous one, so function extensionality becomes provable. Then there's another way, observational type theory. So here we define the identity type by computation. So for example, for identity type of natural numbers is given by these computation rules. So equality of 0 and 0, it computes to the unit type, so or top, or it's true all the time. If it's a successor, the diagonal case, then we recurse. So successor of m is equal to successor of n if m is equal to n. And in the non-diagonal case, we return the empty type, right? So similarly for product types, identity of A times B is an identity in A and an identity in B, and this is also a computation rule. Or for the function space, keep in mind this example, I have that F0 and F1 are equal if I have two equal inputs, A0 and A1, and this F0 and F1 map them to equal output. So this is also a recursive definition, similar in the fashion that we saw for the product type. Okay, and then this talk will be a step towards higher observational type theory, which is not a well-defined type theory yet, but it's work in progress. And here we also define the identity type by computation, just as in observational type theory. But we have this higher rule that the identity for the universe of types, so when are two types A and B identical, we say that they are identical if there's an equivalence between them. So this is a definition of version of Voevodsky's univalence axiom, which assumes the weaker thing that the identity type is equivalent to equivalence. Here we want a definitional equality. So the promises of higher observational type theory, if it delivers, it will deliver an explainable, simple type theory with identity type and univalence. So it would be an implementation of homotopy type theory, which doesn't have interval, it doesn't have built-in geometry, only low-dimensional operations. The identity type or geometry would be emergent, just as there is geometry already built in Per-Martin-Löf's type theory, because you can iterate the identity type and get cubes or simplices that way. It will have computational univalence, so this should be a computation rule, unlike in cubical type theory, which is where it only holds up to equivalence. And it should be a simple extension of Martin-Löf type theory with some new rules. So the current techniques of implementing type theory in an efficient way should scale to that, and hopefully we get an efficient implementation. But this paper is just a baby version of higher observational type theory. So what are the aspects of babiness? So the first babiness, there's no identity type, okay? There's only logical relation, which can be seen. Logical relation is like an identity type, which is reflexive. It's a congruence, so if A is equal to B, then FA is equal to FB for any F, so everything respects identity, but it's not symmetric, it's not transitive, there's no Leibniz rule, there's no general J eliminator for it. And it can also be seen as a kind of abstraction principle. So just as Voevodsky's univalence says that everything preserves equivalences. Whatever you write in type theory, you cannot distinguish equivalent things. And Reynolds parametricity says a bit different. It says that everything preserves relations. So these two principles, neither of them is more general than the other, but they can, sometime in the next talk, we will hear about how they can play together at the same time in certain type theories. But it's also from defining a type theory with internal parametricity is slightly simpler, because parametricity is everything but equality except the transport rule. So we don't have to implement the transport rule. That's why this is the first babiness that we want. Then the next babiness is that in contrast to what I promised at the previous slides, not everything is computational. So, for example, identity type, the rule for identity type, that identity type of A or O B is like identities of A are mapped into identities of B. This is not a definitional equality or a computation rule only up to isomorphism, but this should be easy to fix. Now, the one which is, it seems it's not really possible to fix is that the next one, which I said we would have computational univalence or definitional univalence, so the identity type of identity of types A and B, here it should correspond to relation space instead of equivalences. That's also not a computation rule, and it's not even an isomorphism, it's a section retraction pair. So in our theory, what we have, if we start with a relation, we turn it into an element of the identity type. By the way, this is usually called breach type instead of identity type for parametricity, but for simplicity, I just call it identity. And then you go back, you get a definitionally equal relation, but not the other way, okay? And then finally, we don't even have logical relation, okay? We only have logical span, so instead of a relation, we have a span. So instead of IDA, I have a type for all A, together with two maps into A, 0 and 1, which give you the two endpoints. So this is like the Grothendieck correspondence, fibers and indexed, and we are staying on the fiber side. I will say you some reasons for this, but even in this setting, you can, in this like through the glass looking setting, you can see, or you can imagine how great it will be once we see higher observational type theory face to face. Okay, so now I want to say some technical things. So our semantics is Bézem-Kocan-Huber cubes, cubical sets. So this was the first model of univalence, but they never built a cubical type theory on top of the cubical sets. These are the most natural, or they correspond to the classical cubical sets or classical simplicial sets. They also have a simplicial version. But because if you build the identity type using the interval based on these sets, then the interval becomes substructural, so very weird rules for substitution. And it's difficult. So this is what the category looks like. These are the dimensions, 0, 1, 2, 3. These are lines, squares, cubes, and so on. And then you have lots of maps between them. So for example, for a line, you can get the two endpoints using these maps. So there's a concise presentation of this category by this, which is generated by this two category. Okay, so it's a two category with one object star, which I drew twice, one morphism sock, which goes from this object to itself. Then you have four two morphisms or two cells, this R, 1 and 0. And this here I just composed the successor with each other. And then there are 5 equations which govern this. And then the nice thing is that this diagram generates all of this category. So now I labeled some of the arrows to show how they are generated from this. I won't get into the details, but this is the diagram that we keep in mind. Okay, and this generates our syntax. So our syntax, we don't invent beautiful new syntax out from the top of our head. We just extract it from the semantics. So how do we do that? So this cube category induces structure amplitudes or families on these objects and morphisms of the cube category. So in particular, we have this Prishev model of type theory, and we have morphism of models, sock star, which is precomposition with the sock, which I just called for all, which is exactly the same for all that I showed you before when I said I have spans instead of relations. Okay, and so I have a morphism of models together with these natural transformations. Okay, and then I just call that a syntax. Okay, so this structure is my syntax. I have type theory, a model, and then I extend it with whatever I can read of this this diagram. So for example, because this for all is a morphism, for every context I get a new context, which is the for all version. For every substitution I get a for all. So here for every type, I get its identity type. So for all of A is a heterogeneous identity type because it depends on for all of a context, not in the same context, okay? And then I have these maps. So for example, from the identity type of context, I can go to the endpoints. And from these, okay, so one of the technical comments is that for me, I thought that this type theory is not, you cannot do this, because what are the rules for symmetry? Like, how do I specify how symmetry computes? And the point was, you don't have to specify it. It's just a natural transformation, and that's all. And that's enough, and everything is derivable from that. Okay, but this type theory is still weird because it has an operation on context. You don't want this. So now you have, now you use logical framework, two-level type theory. It's also called higher order abstract syntax, this idea. So now I will generate a new syntax from the exact same diagram, but now it's not from pre-sheaf model to pre-sheaf model for all, but it goes from the standard model, which is internal, to pre-sheaves over pre-sheaves, which I won't explain here. But the syntax that you get is exactly determined by this again. And this is a nice structural syntax. And just very quickly, so for every type, I have for all of A, which is its homogeneous identity type. Only one more slide left. And I have a up or congruence operation, and I have a heterogeneous identity type, which is indexed over the homogeneous identity type and the heterogeneous version of up, and then the same maps and symmetry, and then 5 more equations. Yeah, and then I have some more equations for each type former, which describe how they behave. But this is the essence of the syntax, and it's very like principled. So in summary, we defined in this paper type theory with internal parametricity. In the paper, there are some usual applications of internal parametricity, like the polymorphic identity function example, Church-encoded natural number support induction. And this is the first structural type theory for BCH cubes. So the substitution behaves as it, and variables are as usual. Geometry is emergent rather than built-in, so it's simple, and we prove canonicity. And there is some future work. Thank you.
All right, thanks for the talk. And we are taking questions.
Hi, that was a very energetic talk. Thank you. So I wanted to ask you, so when you have this these kinds of proof-relevant relations or spans, do you get anything like the identity extension property from the relational version, or does it come out differently?
So I never understood this identity extension property, and I read some claims that these kind of theories with internal parametricity, they don't satisfy it, but I think they do, because we are able to prove that Church-encoded natural numbers have induction. So I think we do have, but I don't understand what it is. Yeah. Yeah, I'd be interested. Yeah.
Okay, because we started really late, let's take 2 more quick questions. One more?
There's an online question.
Oh.
So what's the intuition for the notation for all? Like
So I got it from Guillaume Moulin's thesis, who also developed some theories with internal parametricity. But yeah, I don't know. Maybe it should be called EQ, or it's basically the total space of bridge, or like it's a bridge with its parts where it sticks to the side of the river, you know. So what do you call this? So all of the bridge. Yeah. But
Okay, there's one.
So the fact that this is a structural theory suggests that it might be easy to implement in real implementation. So do you agree, or do you see obstacles to implementation
Yeah, so you have more neutral terms. So I think the techniques by Connor, McBride, and others on new equations for neutral terms, those are the kind of techniques that you need to employ. But it should be easy. And compared to cubical type theory, you have where, for example, you need to have substitutions in values, substitutions by interval variables, so that we don't have here. Yeah. So it should be simpler.
All right. So let's thank the speaker again. Right. So the next talk is also about internal parametricity. So it's internal and observational parametricity for cubical egg dot, given by Antoine.
Does it work?
Kind of clip it onto the outside of your pocket. Go.
The slides are not showing up.
Wait a sec. I have to do something for that.
Okay.
Wait a sec. How do you do that? Ah, there you go. Does it work now?
Yeah. So it's just 50. So let me just reintroduce for the online people. Internal and observational parametricity for cubical egg dot by Antoine.
Yes, thank you. Okay, hello everyone. I will begin with a small disclaimer. So in this talk, we will be speaking about pure functional programs with dependent types and presumably within proof assistance. So in this work, we try to answer the question, what is the best way we can provide free theorems to the proof assistant user? And first of all, I have to explain what a free theorem is. So say you have this program here of type for all x to x to x. Maybe you have written it in dependent type theory. You could conjecture that P must be either the first polymorphic projection or the second one. And the intuition behind this is that the program P in normal dependent type theory cannot case on its type variable. And for that reason, it is said to be parametric. But there is also a formal definition of parametricity, thanks to Reynolds. So according to Reynolds, P is parametric if and only if it preserves logical relations. And what I mean by logical relations is really a relation that preserves type structure. So P being parametric means P preserves structure-compatible relations. And for our program P of type for all x to x to x, this relational parametric statement unfolds to the following. So if you have a relation between two types, and if you have x0, x1, which are related by R, and also y0, y1, which are related by R, then the outputs of P must be related by R as well. And in fact, from this relational parametric statement, you will be able to deduce your free theorem of interest. So for us, it was the fact that P must be either the first or second projection. So how do you bring free theorems to proof assistance? There are two solutions that exist currently. The first one is called parametricity translations. And I will only mention them in this talk. And the second one is to have an internally parametric dependent type theory. And contrary to the previous talk, mine are interval-based. Yeah, and so those two solutions actually they offer opposite trade-offs when it comes to incorporating parametricity in proof assistance. So, right, what are they? Internally parametric DTTs. They were introduced a few years ago by Moulin and collaborators. And they are extensions of standard dependent type theory. So you have new types, terms, and equations. And in particular, you have this bridge type around at each type A and points A0, A1. And the basic idea behind bridge types is that they are axiomatic types of logical relations. And it's similar to the path types of cubical type theory, which are basically axiomatic types of isomorphisms. And so in this setting, parametricity is actually the fact that functions preserve bridges. And you have an internal parametricity theorem, which says that for all dependent program, if you have a bridge in the domain, then you have some kind of dependent bridge in the codomain of P. And as you can see, it's definable within the theory, which is very nice. And then if you want a particular free theorem, you can just derive it from this statement, actually. So quantification on the program P is internal to the type theory. That's you need internal parametric DTTs to have that. And this allows you to prove new interesting things when compared to standard type theory. For instance, this Church encoding here. And this is something parametricity translations cannot achieve, actually. There are nice systems available in the literature, but there were no implementation until now. So we decided to look at this system by Cavallo and Harper of their paper Internal Parametricity for Cubical Type Theory. And we decided to implement that system. So the resulting proof assistant, it's called Agda Bridges. So Agda Bridges, it's an implementation of essentially the CH Cavallo-Harper system on top of Agda Cubical. And so the CH system itself, it's an extension of HOT, specifically Cartesian cubical type theory. And Agda Bridges, it's rather an extension of Agda Cubical, which is an implementation of CCHM cubical type theory. So Agda Bridges is the first practical proof assistant with internal parametricity. And in fact, it successfully type checks the cubical library. And so this means that we have nice principles available, such as univalence and Fanext. And so let me quickly describe some of the primitives of Agda Bridges. So you have a bridge interval with two endpoints. You have bridge types, adage type A, endpoints A0, A1. And the rules of the bridge type make it so that bridges are manipulated as functions out of this bridge interval, and also with definitionally fixed endpoints. And there is some subtlety here because we want BI inputs to be consumed substructurally. And this is important for the operational semantics of the CH system to be even stated. And the way we enforce this is via what we call freshness constraints. And so there are basically conditions that are checked on free variable in our type checker. And this is, by the way, an extension of the tick annotation from Agda Guarded. And similarly, you have types of dependent bridges. And dependent bridges, you can think about them as being dependent function over the bridge interval. Other Agda Bridges primitives, you have extent, which given two functions, f0 and f1, and a proof that those two functions are pointwise related, pointwise bridge related, will build you a bridge between f0 and f1. And you also have the gel primitive, which lets you coerce a relation into a bridge. And you also have rules proving that those things are isomorphisms. And by the way, the fact that gel is an isomorphism, Cavallo and Harper call relativity, and it's the relational analog of univalence. And we also redesigned the transp and edge comp operation from Agda Cubical. So have a look at the paper for that. And now we can prove three theorems inside the proof assistance. And I would like you to look at the first line here. So as you can see, it's a proof of the Church encoding for bool. And if you look at this submodule, you can see that we call several parametricity primitives. So for instance, you have the gel type here, you have its introduction rule here, you have its elimination rule here. And now I claim that internally parametric dependent type theory and parametricity translations, they actually offer opposite trade-offs when it comes to incorporating parametricity in proof assistance. So when you do a proof in Agda Bridges, the nice thing is that you have this internal quantification, and so you can prove extra statements such as Church encodings. This is not possible in translations, but on the other hand, when you use a translation, it's an algorithm that computes a parametricity proof, whereas in Agda bridges, you actually have to write the proof yourself. And also, it's not clear how to reuse such naive free theorems proofs in Agda bridges. And so contribution number 2 is our attempt at merging those two methods, and we proceed in 2 steps. First, we go back to the definition of parametricity, Reynolds definition. So parametricity is preservation of logical relations, not just bridges. And so how does that look like in Agda bridges now? We still look at the same example here. So if we want to get back a Reynolds definition for P in that type, if you start with a relation, you can coerce it into a bridge using the gel equivalence here. And then you can use internal parametricity, which is a dependent function, actually. And you get some dependent bridge between P of A0 and P of A1. And then you can get back using an equivalence built out of extent. And finally, you can get what we call observational parametricity. So the fact that actual logical relations are preserved by dependent programs. And what you call the structure relatedness principle is the fact that at all type formers, you have such an equivalence. And this includes dependent types as well. Yeah, sure. So building such the proofs of such equivalences at arbitrary types, it's computationally not easy to do at first sight. And we have reasons for that in the paper. And so we built a library to build such equivalences in a modular way. And so the idea is that types which are equipped with such horizontal equivalences, so types that satisfy the structural relatedness principle, they essentially form a model of type theory. In other words, in order to prove the structural relatedness principle, what you really need to do is only write your type T, a bit like in the parametricity translation ID. And our library to build such equivalences modularly is called ROTT, standing for Relational Observational Type Theory. And I give here a quick example. So how do you use that library if you want to prove some free theorem? The first step is to write the type of your program, or rather the derivation tree of the type using our DSL, basically. So as you can see, I'm using formation rule for the arrow type and the universe. And then you can call param, and so this is the param call. And compared to low-level proofs, proofs done using that framework are more compositional, they're concise and scalable. That's what I claim, at least. And we don't have any automation to extract those derivation trees yet. And also, we don't have support for iterated parametricity, and I don't know if it's possible. I have to think about that. Yeah, and we have more examples in the paper. And this relational observational type theory I was mentioning, it's in a way some semantics, I believe, for the theory we saw in the previous talk, or rather a fragment of that theory. And it's only semantics. We don't have syntax for ROT. It's a library in Agda bridges. And now I will take questions. Thank you.
Thank you. So I believe we have an online question.
Oh, you want me to start with that?
I think so. Yes, please.
Okay, so the naive question from online is, can we translate away internal parametricity constructions and axioms using a parametricity transformation?
So you have to use some kind of reflection to do that, because you cannot have the parametricity translation as a first-class citizen of the language, because that would break parametricity actually. Since logical relations are defined by induction on types, and parametricity is precisely the fact that you cannot case on type variables.
Just to clarify, the question begins with naive question, not that we think the question is naive, okay? Okay, there's a...
Thank you for a nice talk. Could you go back to your slide comparing your system with translations?
Yep.
Yes. So you say that you cannot prove that bool is isomorphic to that with the translation. Can you give a intuition about what's going wrong there?
Yeah. So the reason, if I go back to, this constant here. So in internally parametric DTTs, you have an internal quantification here. So this is like a pi type. And with a translation, what you would get is rather only p on the left of the sequence. So in other words, when you use a parametricity translation, it will only work for concrete programs, for known programs, top-level programs.
So going back to a question from the previous one, I'm wondering if the thing is that the translation does not give you the identity extension lemma.
Yeah, I think this IEL, it's essentially parametricity. I think it's better to state it as internal parametricity. I also actually don't quite understand this IEL thing.
I'll talk with you guys later.
we can take more questions. Oh, here.
Hi there. So you have this church encoding of Booleans.
Yes.
Does it work either at the higher or lower level with index types? So can you do church encodings of inductive families?
Okay, I don't know, but I would expect that it's the case. And we have more complex examples in the paper. For instance, we reproved Reynolds abstraction theorem for predicative system F this time, using Agda bridges as a meta theory, and there, we need to use index types to do that. So,
Okay.
I think we can take two more. Oh, there's a question in the end. Oh.
Hello, thanks for the talk. Parametricity translation is a purely meta-theoretic property on the syntax of the type theory, while you have changed the type theory. So I wonder, can you please comment on the model theory of your type theory? I mean, what's the dilatation semantics?
oh yeah. So this is an implementation of the CH system, and the CH system interprets in bicubical sets, so pre-sheaves over a product of categories. And in our case, this product is CCHM cubes times Cartesian BCH cubes. So BCH cubes, this is the cubes for the last talk.
Right, we can take one more. Here it is. Should I just?
I'm just wondering, what is the subset of types that are expressible in ROTT, and which ones would not fall into it?
So I think the question of knowing if that subset is the entire theory is probably independent. But the idea, and I think your idea, is to make it so that all types are expressible using HOT.
All right, thank the speaker again.
Also, Yi-Yun, if you haven't shared your slides yet, please share your slides.
All right, and the next one will have to be changed to remote, and so I'm going to have to set it up.
If you just arrived, please find a seat.
Hello? Yeah, I think everything is ready, but we want to be synchronized.
Oh, okay, just want to make sure there's no technical issues on my end. Is everything working correctly?
Yes.
Okay.
All right, let's get started. So the next talk is internalizing indistinguishability with dependent types, given by Liu Yiyun. This is the only name I am very comfortable with.
Thanks for the very accurate pronunciation of my name. Hello, everyone. My name is Yiyun Liu, and I'm a PhD student from the University of Pennsylvania. Today, I'm presenting my paper, Internalizing Indistinguishability with Dependent Types. It's a collaborative work with two Penn students, Jonathan Chen, Jessica Shi, and my advisor, Professor Stephanie Wyrick. Let's first start with an oversimplified view of our contribution. Given a system that is dependently typed, if you add dependency tracking on top of it, then you profit. Not all of you are familiar with dependency tracking, and I'll explain what that is shortly. However, what I'll hide away from you throughout the rest of the talk is the many technical issues that you may run into when making this combination work. And instead, I'll spend most of the time explaining why you want to combine dependent types and dependency tracking in the first place. Here's our contribution in more detail. Dependent types allow us to internalize reasoning about program equivalence. In a system with dependency tracking, the type of program equivalence that we're interested in is called indistinguishability. It is slightly more general than the usual notion of a program equivalence, such as beta-eta equivalence, in the sense that it leverages the dependency information and thus allowing us to relate more terms. By combining these two features, we designed the dependent calculus of indistinguishability, pronounced decoy, which internalizes indistinguishability with dependent types. First, what is dependency tracking? A type system that tracks dependency is parameterized over a lattice structure, and the type system prevents the flow of information from a higher level to a lower level. The lattice structure can be instantiated into things that are more concrete and have applications in security type systems, runtime erasure, and staged computing. There are different ways of formulating such a system, and in our design, the typing context and the typing judgment are both augmented with levels, represented by the meta variable L, which ranges over the lattice structure. Let's now take a closer look at a very concrete typing judgment. And here, the term A has type int, with a variable x of type boolean in the context. The level L, colored in green, is the observer level of the term A. It tells us that the term A may only use variables whose levels are less than or equal to L, which is the lowest level. The level H, colored in orange, says that we can only use the variable x when the observer level is H, the highest level. And by combining these two pieces of information, we learn that the expression A cannot use the variable x. Without even knowing the exact definition of the term A, just from the typing judgment alone, the type system ensures that if you plug true and false into A respectively, the resulting terms must evaluate to the same integer value. On the other hand, if we raise the observer level to H, the highest level, then X can be directly used in A. And the early equality we have shown is no longer accurate. Substituting true and false into A might give us terms that evaluate to different results for specific instantiations of A. There's no magic underneath how our system enforces information flow. Here's the introduction rule for variables. And as you can see, a variable x can only be used if its associated level L0 is less than or equal to the observer level. High-level variables cannot be used by a low-level computation, but it's perfectly fine for a low observer to package up the high-level variables and pass them around. As a real-world analogy, let us consider a letter delivery service. We want to send a letter to some recipient, The envelope is locked, and only the recipient has the key to unlock the envelope to access its content. The Postal Service can't access the letter's content, and can be viewed as a low observer in this case. However, the lack of access to the letter's content doesn't prevent the letter from being delivered, because the delivery process is independent of what's written in the letter. We can achieve the same in our type system with box types, or you can also call it by its fancier name, graded model types. Box types enable us to store and pass on the secret in computations with a low observer level. In this example on the slide, the sub-expression x plus 1 is wrapped inside a high-level box. When type checking x plus 1, the observer level gets raised from low to high, so we are granted access to the variable x inside the box. The high-level box can be constructed in a low-level computation, as the example shows, but we can't extract the content x plus 1 unless we have high as our observer level. If we zoom out for a bit, the whole term has a low observer level, with x as a high-level input. We can repeat the same exercise from earlier and substitute two different numbers, 1 and 2, for the variable x. Then the question is, how do the resulting two terms relate? After reduction, we end up with two syntactically different values, box 2 and box 3. But there's more we can say about these two expressions, as the following analogy shows. Recall that the recipient is able to unlock and read the letter, and as a result, they might react differently depending on what the letter's content is. Let's say if it's a love letter, they might react like this. Well, I guess the feeling is not quite mutual in this case. If it's a blackmail, they might get offended because they don't like being threatened. The takeaway here is that for the recipient, the high-level observer, in this example, the two letters appear distinct. On the other hand, the mailman would give the same reaction about the two different letters, because all they can see is the envelope, rather than the content stored inside. In the terminology we are about to introduce, we say that the love letter and the blackmail are indistinguishable from the perspective of the mailman. The different perception of equivalence for different observers is exactly the thing that indistinguishability is meant to capture. Back to our program language, the two different numbers, 2 and 3, when placed inside high-level boxes, are indistinguishable for a low-level observer because they can't use the box content to compute anything that's visible at their level. From a high-level observer's perspective, the box numbers are different because a high-level observer may produce distinct results based on the different numbers stored in the boxes. Indistinguishability is crucial for reasoning about programs in a system with dependency tracking. And so far, we have been focusing on is indistinguishability used in a security-related context. But it also makes sense in other applications such as runtime erasure, where we want to reason about program equivalence by ignoring the parts that are meant to be erased before execution. What's lacking here, however, is a way to internalize indistinguishability in the sense that you can write a program in a dependency tracking system and reason about the program in the same language that they were written. The idea of internalizing equational reasoning is nothing new. We can write down programs inside a proof assistant such as ACTA and Coq, and they use types to state properties about how these functions evaluate. The theorem shown on the screen, for example, states the list append associativity property in Coq syntax. In dependently typed languages, there is an equality judgment highlighted in orange as part of the type conversion rule. We can cast the type of the term to a different type if it is judgmentally equivalent to the original type. The identity type highlighted in blue on the bottom right internalizes the equality judgment, so programmers can explicitly reason about how their programs evaluate. In a system with dependency tracking, we add observer levels to our typing judgment, as we have shown earlier, but we also switch to indistinguishability for our equality judgment. And to internalize this new notion of equivalence, the identity type must be extended with a level index representing the observer level. And by making this change, programmers can now reason about indistinguishability within our dependently typed language. And that pretty much sums up the design of the decoy language, which is an extension of Berenjek's pure type systems with indistinguishability as definitional equality, and also a level index identity type that internalizes indistinguishability. We mechanized the type soundness and non-interference proof in the calc proof assistant, and also provided a prototype type checker in Haskell, so you can play around with the language in a more user-friendly syntax. And of course, now it's time to revisit the question from the very beginning. Why do we want such a design in the first place? One perspective, which is the one we've been focusing on so far, is how dependent types help us internalize the reasoning of indistinguishability. That is useful because of the many use cases of indistinguishability we had mentioned earlier. The old pen and paper proof can now be done rigorously in the program language where the programs were written. A different angle is how dependent types benefit from dependent tracking. By augmenting dependent types with dependency tracking, we gain a different way of implementing compile time irrelevance. Recall the conversion rule in our system, where definitional equality or judgmental equality is implemented through indistinguishability. The observer level doesn't have to be the highest level in the lattice, and when that happens, part of the types that are too high level can be ignored during type conversion. In other words, we can ignore the equality of parts of the two types, A and B, that don't actually contribute to the calculation of A and B. Then how is our system different from the many other systems that support compile time irrelevance? In fact, our syntax of level annotated functions, which I didn't actually show on the previous slides, is actually quite reminiscent of Fanning's system of proof irrelevance or act as irrelevant function types. And to answer that question, we need to go back to the examples about indistinguishability from earlier. If we rephrase the examples in terms of irrelevance instead of indistinguishability, the box numbers 2 and 3 are irrelevant to a low observer, but relevant to a high-level observer. What's interesting is that in both examples, we have the exact same expressions, but we have different views of relevance depending on the observer level we choose. In other words, a level that is higher up in the lattice is not intrinsically irrelevant, but only irrelevant with respect to a low observer. This type of flexibility is useful because it enables us to decouple the relevance of a variable at the type level and at the term level. On this slide, I'm going to show you examples of why we want to have different views of relevance. In the first example, the variable x is directly used in a term because it's returned as part of the function body. But it's not used at the type level since its type is simply a non-dependent function from a function from net to net. In the second example, we have the polymorphic identity function, and the type variable a appears relevantly in the type signature, but only appears as an annotation at the term level, and therefore is irrelevant in the term. And finally, in a constant function from net to net, which returns 0 all the time regardless of the input, the variable x is irrelevant at both the type and the term level. This is probably more closely relates to the more usual notion of compile time irrelevance, where a variable is used in neither the type nor the term level. As a more practical example, let's consider the map function on the length index vector type. In this case, the length index n is irrelevant at the term level because we want the vector type to erase into a plain list to ensure performance. However, the length index n must be treated relevantly at the type level because we want to be able to distinguish between vectors of different sizes to ensure type soundness. From a semantic point of view, the levels do not cause a type to be squashed into a singleton or a false type, but we merely hide information temporarily from a low-level observer. The information is still retrievable if we switch our point of view to a higher-level observer who has access to that information. There's some very subtle ways that this design affects the behavior of our system when it comes to compile time irrelevance, such as the improved support of strong dependent sums, which is in fact one of the more technical motivations. But I guess for more details about the related work, you're welcome to read the related work section of our paper. And that's pretty much it for the talk. And just as a final recap of what we've discussed so far, decoy is a dependently typed language that internalizes indistinguishability. Its design gives us a unified framework for dependency tracking and compile time irrelevance. That's it. Thank you. And I'm ready to take questions.
All right, I believe we have an online question.
Yeah, so the question online is, several frameworks for modal dependent type theories have been presented in recent years. For example, by Andreas Abel, Daniel Gratzer, or by Andreas Nutz. Can your work be presented as an instance of one of these frameworks? If not, what are they missing?
So I think many of the existing frameworks, like model type systems, they actually more or less have the infrastructure to have a type conversion rule that leverages the dependency information that they're tracking. But there are some very subtle issues. I guess the specific system I have in mind is probably it's called, for example, quantitative type theory, where there's a very specific property of the type system that unnecessarily weakens the constraint that your function behaves like a constant. For example, if your function type says it doesn't really use its input, you should really maintain that invariant. But there are cases where, especially in security type systems, where this invariant is relaxed, and if you start doing type conversion, you might run into issues where it just relates two terms that are not supposed to be related. So I think you can say that our system is heavily influenced by the existing development in model type theory. I think most of our contribution is really working out the details to make the type conversion using indistinguishability work in a consistent way, which turns out to be quite tricky.
All right, we can take two or more questions. Oh, exactly, yes.
Hi, thanks for the nice talk. I had, so does your notion of equality, does it have like an eliminator?
Oh, sorry, you mean the, oh, yeah, so the equality is, very, yeah, that has have a, so in the system we present in the paper, we have a transport operator, which is kind of weaker than a G eliminator, but it's pretty much the same equality type from an intentional type theory. If that makes sense.
Hi, thanks for the talk. I was wondering, so it seemed that you only handle PTSs at the moment. That's what I got from the slides. Is there like other fundamental difficulties in obtaining inductive types, even like basic ones like natural numbers, or is it just that it was a simplification made for the sake of keeping the system containable?
I don't think there's any fundamental issues with adding natural numbers, but adding general inductive types would be a completely separate problem. I think with, for example, like natural numbers, there is some very specific problem, which is now that your system has all these annotations for your variables, like for example, when you have features like dependent elimination, like you have to specify what the motive of the eliminator is, and then like what's the level attached to the variable that appears not in the term but only in the motive. Sometimes it can get pretty messy. I think it would still work. I think in that case, the main problem is how to make this type system more usable without cluttering the user with tons of annotations that might not be very interesting.
I see. Thank you.
Okay, we can take one more very quick question. If it's too long, I'm going to have to cut it.
Hi. Thanks for the great talk. I'm curious that your indistinguishability relation seems like that it it has some nice sort of Leibniz equality style properties, but particularly in security type systems, you often end up with downgrading operations like declassification that would completely destroy the sort of Leibniz equality style behavior on that.
Okay, I'm sorry because we have to start the transition then.
Oh.
Sorry. Let's take a question offline.
Okay, sure.
Is that okay?
Yes, that's fine.
Sorry, I apologize for that. So we're going to start a transition so that we can start on time for the next one. I'm really sorry about that.
You can ask in the Discord as well.
I'm going to. All right, we're ready to start the next one, which is polynomial time and dependent types given by Robert Aki.
Okay, thank you very much. So this is some work that is pretty much just putting together two things. So it's one of those papers where you just think, I've got one idea, I've got another idea, and I'll try and do them together, see what happens. And I think what happens is quite interesting. So dependent type theory is a programming language, and some people think that you should be able to write programs in it and actually run them, and maybe one day this is what all programming languages should be like this. And it's also a proof language, so we can write programs and we can reason, but we can only reason really about their extensional behavior. And like we can sort of pretend that we're going to reason about the way they operate because we can encode things. Like we can use monads to sort of surface effects, or we can use tick monads to surface the consumption. But what I'm going to talk about here is a kind of way of talking about the intrinsic costs of programs. So what if we want to talk about a program's complexity? And there's quite a large design space here. So one thing I alluded to there is, are the costs sort of extrinsic, are they user-defined, or are they intrinsic? So do programs consume resources by some kind of tick effect, like we saw yesterday in the decaf work? Or do they simply consume resources just by existing and executing? Do we want to do explicit or implicit accounting? So do we want a statement at the end that says something like, this program takes exactly n squared plus 3 and 12/27 of an n times n steps if the input is size n? Or are we happy with a statement like, this is a polytime program? And another important thing that comes up when doing this within a theory which combines the programming and the proof is, how do we mediate between the intentional and extensional meaning? So how do we stop the costs interfering with the behavior? So if you naively do the thing with the tick effect, then you can sort of end up making the program depend on how long it's run so far. And there's a really clever way of doing that in the calf and decaf work to stop that happening. So in this work, what I've done is chosen a particular space in the design space, which is implicit polynomial time by linear typing, combined with extensional program reasoning with dependent types. And I think this is an interesting combination because, and I think this is sort of possibly slightly delusional, but I think what this might lead to is some kind of synthetic kind of computational complexity theory, where we can do computational complexity theory, but without, I know this is the Turing room, without talking about Turing machines directly or anything like that. So, but there's a question mark. I mean, maybe this will work, I don't know. So this paper is just putting these two things at the top together. So first I'm going to talk about implicit polynomial time by linear typing. So this is quite an old topic, but I'm just going to introduce a way that I'm going to talk about doing it here. I'm going to show you two different ways of doing it. So why are we interested in polynomial time? So probably most of you went to a course on computational complexity, and they said polynomial time is feasible computation. And then you immediately thought, well, what if it's n to the 100? It's not very feasible anyway. But the sort of reasoning that goes here is that feasible computation should be closed under, we're allowed to iterate over the input, right? So take the size of the input, and we're allowed to do a number of steps linearly proportional to that, at least. And we should be able to compose two feasible computations. Like feasibility should be closed under composition, probably. And this one's a bit iffy, nesting of iterations. So it should be sort of closed vertically, if you like, as well as closed horizontally. So let's build a type system for polynomial time, and we're going to use linear types. And the key kind of points here is we're going to separate iterable and non-iterable types, because remember, both the big thing in the previous sort of list of constraints was that we're going to control what we iterate over. So I'm going to have an iterable type of natural numbers at the top there. And you'll notice it's linear, so in the 0 case and the successor case, there's no extra context. We have to, for every information we want to pass through, we have to pass through in the type A, and then we have a natural number, and we can do iteration on it. And let's say we also have a non-iterable nat, so these kind of hollow nats with the little empty circle, and we're only allowed to do case analysis on those. So we're going to separate these two kind of natural numbers. And now, basically, the way to get feasibility is some kind of NIMBYism, right? We're just going to ban construction of natural number values. So we're allowed to construct these hollow naturals that we're not allowed to iterate on. But any natural number that we iterate on must come from the input, must come from the outside. So yeah, we can construct non-iterable natural numbers. We are allowed to duplicate natural numbers. This allows us to nest iterations. So the reason for banning construction is we can't use the input to get bigger and bigger natural numbers. So you can sort of, once you can iterate over the input and you can create numbers, they construct them using successors, then you can sort of define addition, multiplication, and exponentiation, and so on. And a sort of slightly amazing thing is that just with these things and linearity, we get a system that's sound and complete for polynomial time. Let's call this a cons-free system. And a crucial point is that the linearity. So like I said, oh yeah, we can duplicate natural numbers, but what we can't do is duplicate things at higher type. If we could do that, then we could sort of encode constructors in some kind of church encoding kind of thing. So we're not allowed to do that. So this system isn't very much fun to actually program in because you get the natural number or whatever input you have that has some kind of size, and then all you can do is iterate over that. So in theory, yeah, you can do enough kind of steps to simulate a Turing machine, but it's not much fun to program in. So Martin Hofmann, about 25 years ago now, came up with this LFPL system, which stands for Linear Functional Programming Language, that allows transmission of this iterability via diamonds. So we can now construct iterable natural numbers by paying a diamond for each constructor. And then when we iterate over them, we get the diamond back. So in the 0 case, we get a diamond. In the successor case, we get a diamond. And then this allows us to then reconstruct sort of smaller natural numbers underneath that we can then do nested iterations with. And again, this is sound and complete for polynomial time, as long as you also have these non-iterable data structures as well. And also here now, you cannot duplicate the natural numbers. OK, so that's two simply typed systems for doing implicit polynomial time. So the point is that these are both sound and complete for polynomial time. You write your program. If it type checks, then it's guaranteed to be realizable by a particular term that will always run in polynomial time in the size of the input. So how do we combine this with dependent types to be able to reason about programs? And so this is tricky, because in type theory, the variables are used as sort of mixed usage. Some are logical, some are computational, some by logical I mean they're just used there to make sure the types are well formed, but they play no role. So like the previous talk, we have some members of the context which are only there to make sure the types are well formed. They're not computationally relevant. In linear logic, we have things in the context, and their presence or absence means that if it's not there, we can't use it. But if it is there, we must use it exactly once. So we might have something like the X in the type theory context is sort of only used in the types. So then is it really used in the term? Or maybe it's used in the types and the terms. So this makes a kind of naive combination of linearity and dependent types quite difficult. So there's been many solutions to this. I haven't got time to go through them all here, but I'm going to talk about one, which is this quantitative type theory. So the idea is sort of taking ideas from sort of simply typed or polymorphically typed systems where we annotate the variables in the context with how they're used. And we do it from some semi-ring R. So You can do this with, for instance, sets of principles, and you can get information flow typing. Now, Conor McBride's sort of insight was, well, zero usage is very useful here, because if you annotate something with a 0 from the semi-ring, you're sort of not using it in some sense, right? And so this is sort of precisely what's going on when we're just using variables for their meaning in the types. So let's say we allow any kind of 0 usage data to appear in the types. And if you follow through this idea, you come up with a system where, in addition to having annotations on the variables, we have one on the term as well, so this sigma at the end. And this kind of splits the type system into two sort of separate systems. Then when we have sigma 1, this is like the real computational world, and sigma equals 0, it's the types world, the world where we're allowed to do unrestricted computation. And this means that we can do linear typing in the sigma equals 1 fragment, but then there's always a rule that always says if we have something in the sigma equals 1 fragment, we get it in sigma equals 0 fragment, and then we can reason about it there. So I'm going to take one of the systems from earlier, the LFPL one, and combine it with this quantitative type theory. So the first thing we have to do is add diamonds. So we have a diamond type. And now we're allowed to construct diamond type, values of diamond type, but only in the sigma equals 0 fragment. So at the type level, diamonds are free. At the term level, the number sigma equals 1 level, we have to pay for them. And we even have this rule that says this value is unique. So the diamond acts like a kind of unit type. Then, we have to pay with diamonds for constructing natural numbers. And then the important part is this scary rule, which is the eliminator now for these things, which is now dependent. And we annotate the bits, so these red zeros are where we have information which is only available at the type level, but not at the term level, not for the term level. So here we need all these extra gammas around to make sure our types are well formed in all the places. And we're a dependent eliminator, so we've got the 0 and the suck substituted in for the x in the type of the sort of induction hypothesis. And as I said, diamonds are free at the type level, so we can just put star in for the diamond values at these points. And when we're in this sigma equals 0 fragment, all the diamonds are free, so this just acts like a normal NAT iterator. Just want to say the soundness, simplified, is if you have a term like this, then there is a term in another calculus which realizes it and always runs in polynomial time. And for what I want to do next, an also important thing is if we have a term or something that we can construct in the sigma equals 1 fragment, we can reflect that back into the types with this kind of realizability type. So this RA says all the values of A which are realizable within the linear, the sigma equals 1 fragment. So in particular, this is going to mean if A is nat to nat, then RA is going to be the type of all terms which are polynomial time functions from nat to nat. So that means we can then use this system to sort of define some notions from complexity theory. So let's define a problem to be a pair of A in the universe and a predicate on A. So this is like problem instances, and these are decision problems. This is like the ones which are solutions. We can then define p time to mean that there is a decider, f, which is realizable in polynomial time, such that for all instances, if it says true, then the predicate holds. We can also define polynomial time reductions. So if you're sort of looking at this with certain eyes, these are containers. These are sort of like the Cartesian container morphisms. And so it sort of speaks to a general kind of conception of containers as question-answer pairs and container morphisms as reductions between them. But now we're doing it in polynomial time. But OK, we can define p time. That's not unexpected. If we now add the effect of non-determinism, then, and this idea of like non-deterministic computation, we get a witness, a list of Booleans, and maybe it gives us an A at the end, assuming we've got enough Booleans. Then we can define the class NP, right? So we can define it as the problem is in NP if there's a non-deterministic polynomial time computation such that something is in the predicate if and only if there exists a witness that we can supply to the non-deterministic choices. And further, we can define a sort of simple probability finite distributions monad define what it means for that to sort of have what the probability of it returning true is if the leaves are Booleans. And we can define the class BPP of probabilistic problems where it's guaranteed to return the right answer of probabilities at least 2/3. And this is quite sort of shows why we want to combine dependent types and this implicit computational complexity, because we now have to specify this kind of semantic constraint. Okay, so to conclude, what's in the paper? So there's the full description of the systems, a bit about programming, and a description of the soundness proof with its Agda formalization. What next? Some more complexity classes, polytime circuit generators. I think the interesting thing is what is needed for a proof of NP completeness. So the thing here you actually need is to be able to get the source code of the program in order to encode it in 3-SAT. So some kind of extra axioms about this realizability thing. Application to formalized cryptography. We can now quantify over all polynomial time probabilistic computations representing the attacker. And also an extension of the system to explicit resource accounting. So you can actually count the number of diamonds that are being used. Okay, thank you very much.
All right, we're taking questions, and also the question being cut, the author actually responded on Discord, so we take a look. Okay, so we have one question in the middle of the audience, also here.
Thanks for the talk. So I would like to ask, have you thought of connections to descriptive complexity? Because, I mean, there's, for example, this characterization of classes like P, NP, and so in terms of logic. And I'm not an expert in type theory, unfortunately, but I thought if by the Curry-Howard isomorphism or something, there could be some interesting connection with your work as well.
I would like to know, yeah. I mean, like,
thank you.
Yeah, I don't know.
We have one more, but I think this person.
So, have you formalized something is NP complete or something like that?
No, so as I said,
so that's the simplest one that you. First.
So the problem there is that if you want to take I've got a description of a Turing machine which runs non-deterministic Turing machine that runs in polynomial time, then you need the source code of it. So it's you want to sort of take anything which is in that description of NP, get its source code, and convert that into a 3-SAT problem. So it's some kind of reflection required there.
Sorry,
okay. Oh, okay.
So I think around 2015 there was this notion called NP mightiness, which was developed about the simplex algorithm. And basically the idea is that if you look actually inside the bits of the simplex algorithm, it's inefficient, but it's solving a harder problem than the actual linear optimization. And so one of the appeals of thinking about this work to me is that you can actually look inside and see what the intentional behavior of the programs are and see if they're actually working harder than they need to be. So can you look inside of the specific the composition of the specific functions that you're using and seeing what kind of behavior they have themselves?
No more than you can by the fact it's a program and you can look at the source code.
Okay.
Yeah. The types are kind of like everything says just this is polynomial time. It doesn't tell you any more information. Maybe with the explicit one, maybe.
Yeah.
Okay.
If it's a student, I can.
We already have like 3 and 1 more question in queue, so yeah, just continue. Oh, you're fast. Who is the next name? No, the online come after them. Yeah, sorry. Well, our queue is already full. But we can. You're encouraged to continue the conversation on Discord, and I believe Rafa will take a look.
If I had a more restrictive idea of feasibility, where I thought n was feasible, but n to the 500 was not feasible, is there a way of, would it be easy to extend this to index the types by giving an actual count of how nested the iterations are?
I thought about it briefly. I think so, and it gets incredibly fiddly. But yeah, I think so. Like you basically have to annotate the types involved in the iteration to stop you when you've gone too far. You're not allowed to nest them too much.
I think we can take one more because there are no more talks after.
I just want to ask briefly about your comment that it's not very much fun to program in calculus. I mean, the criterion of sound and complete for polynomial time is pretty coarse because you can just, to simulate a Turing machine, you just need bits. You don't need any kind of interesting data structure or anything. So how far do you think you are from capturing natural polynomial time algorithms, and is that an interesting direction for the work you're doing?
I think it is an interesting direction. I think there's been quite a some sort of practical work using LFPL to actually program with. So it was actually in the context of the fact that you can also interpret the diamonds as memory cells and it's all in place. And there's work on writing like reasonable programs in there. So you can write sort of sorting algorithms and things quite easily. Whether you could get a good library of polynomial time things, I don't know. Yeah. But yeah, I mean, yeah, to actually use this, I mean, the point is that when you can do these polynomial time reductions, you actually want to write things you're interested in. And programming with graphs in functional languages is already a pain anyway. So maybe this is the if that's the kind of thing you're doing.
All right, let's thank the speaker again. So that concludes the session. I believe the next thing is lunch.
Yeah, so lunch will be upstairs, so everybody just
Good afternoon. Welcome to the medley session. So we have 4 very diversified and exciting talks. We just don't have a common title to summarize all of them. Let's start from the first one, guided equality saturation. Our speaker is Thomas Collet. Go ahead.
Thank you. So this is joint work with my colleagues Andres, Sira, Tobias, Phil, and Michael. And Michael and Andres are here with us, so don't hesitate talking with them later. I will start with an example, which is about reducing memory usage in a functional program. So let's say that you want to do this by introducing the rewrite rule on the left, also known as map fusion. And you want to apply this rule on the program that is shown on the right. The problem is that you can't directly apply this rewrite rule because the left-hand side of the rewrite rule is not in this program. But we can do something about it. We can add 2 more rewrite rules. So rewrite rules 2 and 3. And even though they have no effect on memory, they still allow us to reduce memory usage because they enable applying the first rule after applying them. So on the right, you can see that rule 2 and 3 are applied, and then that allows us to apply the first rule twice. The problem is that this rewrite path, it will not be explored by a technique like greedy rewriting because the memory is not reduced by these rewrite rules. So there is no local progress. So what we can do is using equality saturation instead of greedy rewriting. The idea of equality saturation is to perform the rewriting on an equivalence graph instead of an E-graph, or E-graph, sorry. When we initialize it from the input term, it looks a lot like a standard abstract syntax tree. But it becomes interesting when we apply a rewrite rule for the first time. So here we apply the second rewrite rule, and instead of replacing the left-hand side of the rewrite rule with its right-hand side, we simply record the equivalence between the 2 sides. So as is written on the slide, transpose map map G is equal to map map G transpose. And that's why now in the graph, we have an additional node which is in the same equivalence class as another node. So here the equivalence classes are represented by these dashed boxes, and the solid boxes are almost regular nodes. We can keep applying more rewrite rules in this way, and at this point the E-graph efficiently represents many equivalent terms because it is doing a lot of sharing. So we have a lot of nodes that are referring to the same equivalence class, and each equivalence class encodes many equalities. So if we want to finish optimizing our program with equality saturation, we need to extract a term from this E-graph. Here we are going to extract a term that minimizes memory usage. And it turns out that it's the term that we had on the slide earlier, the global optimum map map FG transpose. So equality saturation has a lot of benefits because it allows us to explore past the local optimum compared to greedy rewriting, but it also has its own limits. And we can see them by complicating the example a little bit more. So now, instead of simply reducing memory, we're interested in applying an additional optimization, which is known as tiling. And that, to be brief, is used to improve memory accesses. So we add rule 4 and 5. And now we can perform things like one-dimensional tiling. So one-dimensional tiling is very easy to apply using equality saturation. If you look at the graph on the right, which shows the memory footprint, you can see that we're not using even a megabyte of memory. and a single iteration of equality saturation is sufficient. So what is an iteration here? An iteration is when you apply all the possible rewrite rules to the E-graph once. So typically, equality saturation works by growing the E-graph iteration after iteration. So one iteration is very simple, but we can make it more challenging by increasing the dimension of the tiling. So if we want to perform two-dimensional tiling now, this becomes more challenging. So before, only applying the fifth rule was sufficient to achieve the tiling. But now we have to combine the fourth and fifth rule with the first ones to achieve our goal. As you can see with the colors, the transpose functions are coming from the fourth rewrite rule, and the split and join functions are coming from the fifth rewrite rule. Now we can, if we look at the memory footprint of using equality saturation to achieve this goal, it takes 6 iterations, and we are using a couple of megabytes of memory. And when we go to the third dimension of tiling, that's when things blow up. So now, after 8 iterations of equality saturation, we observe that the E-graph grows extremely rapidly. And in fact, we exceed our 8 gigabytes of memory without finding the goal that we're looking for. So this shows that while equality saturation is very powerful, it can also be very expensive when you try to scale it out. So to summarize the problem, we are trying to achieve a final goal using equality saturation, but we are running out of resources before achieving our goal. So what can we do about it? And that's where our technique-guided equality saturation comes in. So the idea is that if you are not able to achieve your goal with the fully automatic equality saturation, you can ask an expert to provide guides or intermediate goals, and in this way break down a complex equality saturation search into a sequence of easier equality saturation searches. So now, instead of failing to find the final goal, we can find it thanks to the intermediate goals. What does this look like on the 3D tiling example? So at the top of this slide, we still have the same program that we started from in the 3D tiling case earlier. But now, instead of trying to directly find the tile program at the bottom of the slides, we are introducing this intermediate step. So the guide here provides the insights that to apply tiling, it's actually easier to first split the maps before reordering them. So we are decomposing this optimization in 2 stages. And actually, a guide does not have to be a complete term. So we allow guides to be more or less precise sketches. And you can think of sketches as incomplete programs. We still guarantee preservation of semantics because we are still applying semantics preserving rewrite rules. So we don't need to worry about allowing invalid programs using this guide. So with these single guides, we actually make 3D tiling reachable. On the left, we have the unguided search, which was using more than 8 gigabytes of memory and failing. And on the right, we have the guided search. So now we actually have 2 equality saturations that are running. The first one takes 6 iterations to find the intermediate goal. And the second one takes 7 iterations to find the final goal. So we can scale this our approach even further by looking at matrix multiplication optimizations from a compiler which is called TVM. So TVM is a specialized compiler for machine learning, and it has a tutorial in which they explain how to optimize matrix multiplication in their framework. So with TVM, the optimizations are also not fully automatic. There is also some form of semi-automation. And the optimizations that are applied include tiling, which is about transforming loops, but also other optimizations that change data layout and add parallelism. There is prior work that already showed that it's possible to express these optimizations by manually composing rewrite rules. And now what we're interested in is automating this process using guided equality saturation. So these are the benchmarks for unguided equality saturation. Here we have 7 optimization goals of increasing difficulty. So the baseline is very easy to find. The blocking goal is similar in difficulty to the tiling goal that I showed you, but this time on the bigger program because it's matrix multiplication. And then we have more and more complex optimizations that are layered on top. And we can see that the 5 most complex optimizations for matrix multiplication are too hard to find without guidance. You can also see on the right how the size of the E-graph grows extremely rapidly, as we've seen before. Now, if we use our guided equality saturation technique, we can find all of these optimizations with at most 3 guides. And each guide is eliding about 90% of the complete program, so it's 10 times smaller. We can also compare the runtime and memory consumption for the second goal, because it was the most complex one that was found without guidance. And with a single guide, we are actually able to find this optimization 582 times faster using 116 times less memory. We have a second case study, which is about showing that we can go beyond program optimization with our technique, and actually implemented a tactic for the lean theorem prover. And what is nice about this tactic is that it allows you to write your theorems by focusing on key reasoning steps. So here, the blue box is guides for our technique. And compared to the proof that you would have to do if you were applying every rewrite rule by hand, this allows you to omit a lot of steps and details. So you don't need to mention which rewrite rules you're using, and everything that is in green here is inferred for you or discovered for you. We pushed this to slightly more complicated theorems. So we prove theorems on rings of characteristic 2. For the theorem on the left, you guided and manual techniques. And we can see that the guided technique is much faster than the unguided technique, but at the same time has a negligible overhead compared to manually providing all of the rewrite steps. For the theorem on the right, we compared what happens when we change the amount of guides. So we had, initially, we came up with 5 guides, and we decided to see what happens if we don't use some of these guides. So we tried all the combinations, and it turns out that actually 1 good guide is enough. So it's very important to choose your guides wisely. To conclude, guided equality saturation offers an effective trade-off between manual and automated rewriting. For program optimization, it enables expressing optimizations with guides that resemble explanatory code snippets. So something you might do when you're writing a paper and you're trying to explain your optimization to other people. And for theorem proving, the guides resemble the key reasoning steps that you might find in some textbooks. If you're interested, we have more details in our paper. We also have supplementary material with all the programs and the guides that we used for these experiments. And our code is open source. Thank you.
Hi. one of your examples is the Frobenius morphism in a field of characteristic, or in a ring of characteristic 2.
Yes.
Of course, it generalizes to rings of any characteristic, but would this have an impact on the complexity of is there something in the characteristic of the ring that would impact the performance and the speed of the approach?
So are you talking about proving it for different instantiations of the characteristic, or
yes,
for a generic characteristic?
For different instantiation of the characteristic, would it change execution time? Would it increase execution time? Does it depend on it?
Maybe Andres can answer this question. So Andres worked on the theorem proving case study.
Yeah, thanks. As a disclaimer, that was just to find an example where you needed a bunch of rewrite rules. I presume it would not change that significantly because you just have a different. So you can encode that as one rewrite rule where you say basically 1 + 1 is 0, and if you have a different characteristic, you might get a few more. But yeah, I don't think that would. It's obviously, yeah. There's obviously much easier ways to do this. This was just to have a large set of rewrites to test it.
So, question here. So I was wondering whether these intermediate human-provided guide sketches that you have, do you know if they have any particular property that distinguishes them, which one could search for automatically? Do they have any, even though they may not immediately be clear how to find them, are there characteristics that you know about what they should satisfy?
I think that's a good question. And so the first answer I would give is that the entire point of allowing the user to provide these guides is that in the general case, we don't know how to find them. And to find them, you need domain-specific insight. But I think that there is definitely interest in automatically finding these guides for specific domains. So for example, if you think about tiling, you could easily automatically infer the tiling guide if you know that in the specific rewriting problem that you're looking into is about tiling.
Hi, right here. Thank you for the talk. I'm really excited by this work. I was wondering whether you could comment on how much your method relies on the particular framework that you use for quality saturation. And in particular, I know recently there has been some work in implementing equality saturation in data log, and wondering whether your technique could be ported to that.
Yes, that's a good question. I think there is no fundamental reason that prevents you from applying this technique in another equality saturation implementation. And actually, I think there are even many more opportunities if you think about the data log implementation, because there is an implementation of equality saturation called egglog, which is about implementing equality saturation using database theory. And I think that it would be very interesting to think about expressing guides as database queries. So I would say it's possible, and maybe even allows even more a richer language of guides.
So one of the advantages of sketches, in addition to just, you don't have to think as hard because you don't have to think through all the details, is reusability, right? The fact that if you have lots of problems that kind of share similar structure, they can all share the same sketch. But sometimes you have to engineer these sketches a little bit if your goal is reusability. I wonder if you can comment a little bit on this.
Yes, that's a good question. So actually, I can quickly show that we have some sketch abstractions that we use in our experiments. So here, for example, without going into the details, we have this def contains add mo, which defines a sketch by composition. And we have also defined other sketch abstractions in this way. So although for different performance optimizations, you will write different sketches. You can still define abstractions by compositions and reuse them in your different optimizations. And I guess the second, beyond these abstractions, we also noticed that for the different optimizations that we are looking at, we have a lot of intermediate goals that we can reuse. So we don't have as many sketches as the sum of the sketch guides in this table.
We have last question there.
How do you see apply this work in a rewriting system with backtracking?
Can you elaborate on?
Well, you talk about greedy rewriting.
Yes.
And when if you I don't know, use some sort of backtracking, you can certainly say that I solved part of the phase scheduling problem.
So I guess there are. Yeah, maybe we can. I can answer this question after.
Sorry.
All right, so let's thank the speaker again. So the second talk of the session is from a group of researchers from Peking University and the University of Science and Technology Beijing, Longyan University, on fusing direct manipulations into functional programs, and Xin Zhang will be our speaker.
Hello, everyone. Hello, everyone. I'm Xin from Peking University. Now I will introduce our work fusing direct manipulations into functional programs. Live programming enables developers to see real-time output changes while coding. Look at the left-hand program. After modifying the variable w to 20, the output rectangles changes immediately without re-executing the program. However, we can only read the output. A further step is bidirectional live programming. It allows developers to edit the output and reflect those changes to the source program. For instance, we manipulate the rectangle's size to twice and reflect it back to the left program. The variable w automatically changes to 20. So in that way, we run this updated program again, we will get the rectangle just manipulated. So there are two types of bidirectional live programming systems. One is state-based systems. They are only concerned about the updated output snapshots. Suppose that we desire a yellow rectangle. The first option is to directly modify the colors, and the second option is to delete the old one and draw a new yellow rectangle. So state-based systems just see the same result of these two operations. So both operations will result in the left-hand same updated program. The other is operation-based systems. They consider more information about the manipulation processes. For instance, directly modify the color will result in directly modify the color parameter in the program. In contrast, deleting and then drawing will result in the deletion and insertion of the list elements. So as you can see, operation-based systems can offer developers more control over program modifications. There are several existing operation-based systems. A notable system is Sketch and Sketch by Ravichu's group. Although they provide a series of powerful direct manipulations for SVG graphics, like alignment and grouping, these manipulations are code sensitive. Through trace links between source program and its output, they perform hard-coded program modifications for each direct manipulation. making it hard to extend. Besides, users need to understand the source program when they use those direct manipulations. So it's less user-friendly for UI. Therefore, what we want to do is to separate direct manipulations from the source program. That's why we designed a delta language to express direct manipulations. Then we define a kind of fusion that can propagate a delta written in the delta language into the proper positions in the source program. We call this approach code insensitive because if developers desire to extend more customized manipulations, they can use these delta languages to write them. They don't need to care about any program modifications. Additionally, direct manipulations are now defined for output values rather than the source program. So UI designers can only focus on the visual output, making it suitable for collaborations between the programmers and UI designers. To sum up, our main contribution is to present a new operation-based framework for BLP systems called FuseDM. Specifically, first we design a simple and expressive delta language, which is simple to be fused to the source program and expressive to encode common direct manipulations. Second, we present a fusion algorithm that can propagate the direct manipulations into the general purpose functional programs and embed it into the proper positions. So we also prove its correctness, which means the program fused with a direct manipulation can run again to get the output that is applied by that direct manipulation, right? So third, we implement an application, a prototype SVG editor. We have successfully worked out 14 non-trivial benchmarks. Okay, this video shows creating a ladder using our tool, starting from a blank code. On the left is a code editor, on the right is an output canvas. Oh, let's start. So we can draw and copy some graphics and connect vertices of them. Group them, align them, and make them equidistant. So finally, we get the left-generated code that can produce exactly this desired graphic. Now let's start to explore the delta language. This is a subset of deltas denoted as dv that act like functions or operations on values. Let's begin with simple constructs. The simplest one is identity, which keeps the value unchanged. These are the arithmetic deltas. For addition, if we apply plus n2 to n1, then we get n1 plus n2. It's easy, right? Multiplications are similar, so if we want to change 5 to 10, there are two options. Well, the first one is to plus 5. The second is multiply 2. These are two different options. Will perform different program modifications. Furthermore, we have deltas for data structures. Take tuples, for example. Applying a tuple delta will to a pair of v1 and v2 means applying these two subdeltas to the subvalues respectively and combine these updated subvalues again. We also have compositions where we apply delta 1 and delta 2 to the value in turn. So for lists, we design a special delta called list folding to update list elements from left to right in a recursive way. For instance, we want to add 1 to each even index elements. So we set the accumulator as 0 and write the derive and to delta functions in this way. This list folding will produce +1 for each even index elements and +0 for each odd index elements. Finally, we obtain 2, 2, and 4. Note that this list folding can update lists at an arbitrary length. It is different from this constant one. You can imagine that in program modification, this list folding will insert a recursive function, while this constant delta uses a more hard-coded way. So actually, they represent two different modification intentions. We can even create relationships between subvalues through constraint introduction. For example, we want to make the second element of this tuple to twice its first element. And we can write the delta in this way. The main part is a tuple delta, where ID keeps the first element unchanged, and the second part, REPL, replaces the original value B with an entirely new value 2x. So what is x? It's a newly introduced variable defined in the delta's prefix, and so it points to the first element. Through this constraint introduction, we achieve the result, a pair of A and 2A. This constraint introduction is different from directly replacing the second element with a constant value 2A, because the constraint introduction implies an underlying relationship. So we use our delta language to encode a series of common direct manipulations listed in this table, such as copy group and equidistant operations, to demonstrate the expressiveness of our language. If you are interested in the details, you can see our paper. Now we have the delta language. The next step is to consider how to fuse the direct manipulations into source programs, and where are the proper positions to embed direct manipulations. In bidirectional live programming, developers do not want a too big modification to the program, because it's hard and time-consuming for them to understand that. So we pursue local and small modifications. Specifically, we try to propagate the delta into the deepest substructure of the program, such as constants, implying that the modification is local and small. I will show what local and small mean. Consider fusing this left delta into the right program. We call the left solution non-local modification because it just puts the delta outside of the whole program. This is really not what developers want. In contrast, we call the right solution a local modification because it propagates the delta through the program structure and decompose it into smaller ones to be applied to substructures of the program, making the modification to be local and small. So this is what our fusion algorithm can achieve. I use a tree to represent the program and show the intuitive fusion algorithm. The fusion follows call-by-value evaluation steps, starting from the program root. It propagates the delta through several function applications and decomposes the delta when encountering data structures. But the propagation stops here because the variable n is updated by inconsistent deltas. And this is exactly what we define the proper positions. So we embed multiply 2 to the left n to get n multiply 2. And embed the identity to the right n, which is still n. And finally, we get the left-hand updated program. These are the formulation of the fusion algorithm. We prove its correctness. You can find more details in our paper. To demonstrate the effectiveness and usefulness of our fusion algorithm, we implement 14 benchmark examples from Sketch and Sketch using our tool. 2 videos have been prepared. One is a tutorial and another shows the detailed processes of implementing 14 benchmark examples. They can be found in our artifact package. In summary, we have 3 contributions. First, a simple but expressive delta language. Second, a fusion algorithm that can propagate direct manipulations into proper positions of the source programs. Third, an application with designing 14 non-trivial benchmark examples. That's all. Thanks for listening.
Hi, Xinjiang. Thanks for the nice talk. I'm curious if you offer any guarantees in the fusion algorithm for the minimality of the incremental change. Like, if you make a change, 2 changes in parts of the program that are far apart, maybe.
Sorry, can you speak louder?
Yes. Is there any guarantees, basically, about the minimality of the incremental change that you have to recompute?
The first word is what?
Do you find the smallest possible change, or are there perhaps smaller ones that the fusion algorithm might abstract?
Okay, I'll use this diagram to show. So for the local and small definition, we mean we just mean somewhere we cannot continue to propagate it. So we think it's the deepest substructure. And the other options, because they are far from the substructure. But we just define the deepest in our algorithm, not in any strategies. Yeah, so there is somewhat no formal definition or no for the small mean.
Thank you.
Okay.
Hi, thanks for the talk. Oh, I'm over here.
Hi.
I had a question about, I was wondering if you could elaborate a little bit on how you infer the deltas from the user's manipulations. Like if I were to drag the corner by 10 pixels, how do you know if that's a +10 or a ×2? And just maybe for more complex cases as well, like list manipulations, how much do you rely on user input versus some kind of inference algorithm?
Actually, it's not inference. It's the responsibility for the 2 developers. For example, if there are 2 UI interactions, if we click multiply 2, and we think this is a delta that multiply 2. And if we directly drag the corner, we think it express plus delta. We just use different UI interactions to express different deltas.
Okay, thank you for the very good talk. And my question is, you mentioned something about the correctness of the algorithm. Can you elaborate a bit more on that? What do you mean by correctness?
Correctness means, so you know, we fuse direct manipulation into the program, right? And the correctness means the program fused with that direct manipulation run again to get the output, that is the original output being applied by that direct manipulation. Okay?
Okay, let's thank the speaker again. So our next talk is on inference of robust reachability constraints. And our speaker is Yanis Selami.
do not have any. Okay, great. So thank you for the introduction. So today I'm going to present to you our work on the influence of robust reachability constraints, which we did with my colleague in CEA. But let's not talk about influence of robust reachability constraints immediately. Let's start with a very simple, very boring example about program verification. So of course, programs have bugs. For example, here we have a very uninteresting program where you are going to feed into two variables A and B some values. And then it so happens that if you sum the two values and that the sum is equal to 0, then there is a bug. And of course, if you have a bug, you can exploit it with a vulnerability. And we need automated method to automatically detect such bugs. So there are automatic methods to detect some of these bugs. For example, symbolic execution, when you're going to explore the program path and find possible inputs that are going to lead to these specific cases. There are other possibilities, bounded model checking, for example. And for example, here, this technique is going to tell you that if A and B are both equal to 0, then you have a bug. And as the technique is sound, so you have no false positive, you say, okay, so I have a bug, I'm very happy. If I am an attacker, I'm very happy, I can exploit this bug. But maybe it's not that easy. Maybe you're more in the context like this, where instead of feeding the two variables, one of them is uninitialized. Here, for example, B. And in these cases, if you still ask your symbolic execution engine, it's still going to do that, to say that triggering the bug is still very easy. You still have to put A and B equals to 0. But then as an attacker, if you try to reproduce or replay this bug, it's not going to happen. You're not going to be able to set the specific value for B, and so you're not going to be able to reliably trigger this bug. So, of course, this is a very uninteresting example, but there are a lot of practical causes of unreliable assignments in programs, interaction with the environment, stack canary, uninitialized memory, etc. And so we need a methodology or a method to evaluate the practical replicability of bugs. So what has been proposed previously for this is a possibility is to use robust reachability. So what people do with robust reachability is they partition the input space between the one you can control as the user and the one that you cannot control as the user. So here you control A because you're going to feed it a value, but B is uninitialized, so you don't control it. And you focus on the finding unreliable bugs by setting a different type of quantifier between those variables. So you're setting an inexistential quantifier in the value you control and a universal quantifier in the value you do not control. And doing this, you say that in our case here, you're very happy because as B is uncontrolled, there is no value to feed in A that is going to reliably trigger the bug independently of the value of your uncontrolled input. So you're happy with this. You have extended reachability and provided tool for this, but maybe this is still not enough. Maybe you have this type of problem here, so the exact detail of the constraint is important, but you have memory copy function that does two things. There is a slow and a fast pass. So the idea is if you're slow, you can copy the bytes one by one. And in some cases, you can copy word by word, so several bytes each time. And the important part here is that the fast pass is buggy and the slow pass is not. So you have this program where you have a part that is buggy and a part that is not buggy. So of course, as there is a bug, your reachability constraint is going to tell you that this is a vulnerability. But as it depends on a memory alignment constraint, robust reachability is going to tell you that no, if you want to find a value that you control that is going to work independently of the value you do not control, so here the exact addresses of your buffers, then it's not going to be robustly reachable. So you're not going to be able to reliably trigger this bug. But as you have an alignment constraint, memory alignment constraint, it's still going to happen a lot of times. So what you need now is the ability to characterize these cases that are in between simple reachability and complete robust reachability. So to do that, what we propose to do is to look for robust reachability constraints, which we defined as predicates on the program input that are sufficient to have robust reachability. So here, for example, you're going to set this as the alignment constraint. You have to have both your source and destination buffer, the addresses, aligned on 32 bits in order to trigger this bug. And if you have this, you have the advantage that it's already part of the robust reachability framework, and that it allows you for a more precise characterization. So now, the idea of our work is to find a method to automatically generate such constraints. So briefly, the contribution of our paper is that we propose an algorithm to be able to generate such constraints, which is based on a theory-agnostic abduction algorithm. And we propose a very efficient optimization in order to have this work in practice. So the idea is to find a predicate on your input memories that guarantees the reachability of a given prescription. So a bit of background on abductive reasoning. The idea is that you want to find a missing precondition of an unexplained goal. So there are already a lot of work that has been done on abductive reasoning, both in logic and for program verification. So either in theory-specific abduction settings or for specification synthesis. What we're interested in here is the theory-agnostic abduction algorithm that provides efficient procedures and genericity to handle a wide range of problems. So our goal here is to adapt such algorithm at program level to be able to generate a robust reachability constraints in this context. So now, how do we do this? It's fairly easy to obtain. So we have a baseline procedure that I'm going to present here. So we take, of course, our program and our target location or predicate we want to have in our program, and a memory partition between the inputs we control and the one we do not control. As we are going to be theory agnostic, we are going to base our generation on a different language, which you can basically see as a set of candidate solutions we are going to try. And so what the procedure is going to do is first select a candidate, try to see this candidate is a possible robust reachability constraint. If it is, you have a solution, you're obviously happy. If not, you're going to try to obtain information from this failure case in order to obtain a more efficient generation. And how do we test that candidates are constrained? In order to keep our generic proposition, we are going to do an abstraction with Oracle for robust and non-robust properties that can accommodate a lot of different tools, such as symbolic execution, model checking, etc. So you get a baseline algorithm. The idea with this algorithm is that we have some properties depending on the properties that our oracles are going to have. So of course, termination, correction, and some completeness with respect to what we put in our inference language. And if we have all the good properties with our oracles, we can also have a minimality and a weakest constraint generation, which means that if you have the weakest constraint possible in your inference language, you will be able to generate it with this algorithm. So now, of course, as this is presented as an exhaustive exploration of an inference language, it's not going to be very efficient. So what we do is propose a set of strategies adapted from other work and improved with the genericity we have here in order to make this applicable in practice. So I'm not going to present all of them here, but some key points on what we are going to do. First, we can use necessary constraints. So the setup is we have a candidate. It's not a sufficient candidate, so it does not guarantee the reachability of our constraint. But maybe we can use an additional non-robust test to say that the constraint we tested is actually necessary in order to obtain our goal. So we will not be able to have our goal or our bug without this constraint being verified. So what we can do is add this constraint to the following constraint we are going to test. And by doing this, we can build a candidate solution that is going to be more precise, faster than if we had to do the exploration. This is something that we can do to emulate what you could do with an SAT core usage, but in the context of generic oracles. Now, the other thing you like to do when you explore inference languages is to be able to use and reuse counterexamples. So here, it's the same context. You have a candidate that is not sufficient, but what you say is that maybe from this information you can know that future candidate will be able to be eliminated from your candidate set without the ability to, without the need to test them. However, as we have a quantification, it's not going to be that easy to obtain this algorithm. So what we propose is to use an alternative property on the program in order to obtain counterexamples. And when we satisfy the satisfiability of the following constraint with those counterexamples, we are able to prune them from our set of candidates. So now, of course, we did some experimental evaluation of this. We tackled binary programs or compiled programs. So we did this with a restriction of our genericity with an implementation of symbolic execution and robust symbolic execution based on BinSec. We did a prototype, and we evaluated this on 2 benchmarks from software verification and security evaluation. So the first idea, to give you just an idea on how we are able to generate the constraints. So we tackled fairly simple inference language with equality, disequalities, and inequalities between memory bytes. And what we show here is that we are able to generate more constraints that permit the robust reachability of the case, which is more than what you could characterize with only robust reachability. And that also among them, you can find constraints that are weakest constraints, which means that you have correctly characterized the whole set of inputs that permit to reach the bug you have set. So we did some evaluation to show which one of our strategies were able to improve or not our efficiency. What we show is that all of our strategies can improve the efficiency. But what's interesting is that each of the strategy we had actually impacted a different part of the algorithm. So some of them managed to obtain a candidate solution faster. Some of them permit to reduce the size of the inference set. And some of them permit to get good candidates faster than others. And after that, what we did is some kind of vulnerability characterization in a security evaluation task. So here the idea was to have a fault injection benchmark. So mainly you evaluate a program that is not going to be executed correctly by the engine. You're going to fault the program during the execution. And by faulting the program, you're going to be able to change in behavior and introduce bugs. And what we wanted to do was characterize which of these introduced vulnerabilities were serious or not. So if we had only symbolic execution, we could find that 1,700 of these faults were introducing a potential formal vulnerability, but we were unable to see if they were serious or not. If we had only robust symbolic execution, we can find 118 cases that are very serious and very dangerous, but some of them are still serious. If we do a projection of the constraint with what we had, so to give mostly a proportion of inputs that are vulnerable, we see that with some of the constraints we generate, even more than 5% of the inputs are vulnerable. So we need to have this characterization. So as a conclusion, what we can say is that we propose a precondition inference algorithm that helps to characterize and improve the notion of robust reachability, that is built on an adaptation from theory-agnostic abduction algorithm, but applied at program level for exist4 quantified formulas. And we demonstrate its capabilities on simple yet realistic vulnerability characterization settings, so either in a software verification or security scenario. And what's interesting here is that we have preconditions that can explain the vulnerabilities that were introduced, so we can afterwards reuse in order to do additional work, for example, comparing vulnerabilities, understanding them, etc. So now I'm open to a question if you have some.
from a high-level point of view, it looks like you're doing some form of approximate quantifier elimination over the semantics of the program, with the controllable inputs existentially quantified and the other ones universally quantified. Can you comment on the relationship between the two?
So the idea is that you can have if you have a relation, what you do not want to do is generate constraint on your existentially quantified constraints, because you are already going to explicitly specify them with the execution engine. But what you can have or need at sometimes is a link between the controlled and uncontrolled variables. So the algorithm is able to generate such constraints, but it's not perfectly adapted, because you are going to have some difficulty to prune some of these constraints if you put them in your inference language, due to the fact that you specify and explicitly characterize the controlled variables.
Thanks for the talk. That was really interesting. Once you've got a candidate precondition, and then you need to test whether this is sufficient. The property you're testing obviously has a mixture of existential and universally quantified variables. So does the procedure that you use to test whether this is sufficient have a mixture of, say, symbolic execution and traditional program verification? Because if you have no controlled variables, then you're doing like program verification. If you have no uncontrolled variables, then you're doing bug finding, like traditional bug finding. So how do you combine those two procedures?
So the actual tool we use does forwards these problems to the SMT solver. So basically, you do a symbolic execution. You explore the path like you would for direct symbolic execution, and then you universally quantify the part of the memory you have defined and controlled. And you just send that to the SMT solver, and you get an answer from that.
So does this depend on there being a limited form of recursion in the program?
Not really. It depends on the ability of the tool you're going to use. But you can also reduce part of the algorithmic generation of your constraints if you want to. It's not.
Okay, thanks.
Thanks for the talk. It was really interesting. Robust reachability and symbolic execution and things like these, robust reachability applied to symbolic execution, this allows to have a whole bunch of optimizations when executing the program symbolically. How does this play out in this case? Can you use the inferred constraint while executing the program in order to prune part of the search space, or is it not possible?
That's what we would like to do, but it's not done actually.
Okay.
But yeah, it's part of the idea to go further, either to simplify the constraints you're going to send to the oracles, or to go inside the oracles to help them guide their search with some of the constraints you can generate.
All right. If no more questions, let's thank the speaker again. Last but not least, of course, is one of our distinguished papers on nominal recursors as epi recursors. Our speaker is Andrei Popescu.
Thank you very much. Welcome to my talk. And thank you for the introduction. I thank the committee for the award. That's really honors me. Hope my talk will not disappoint. So I'm going to talk about these wonderful things called nominal recursors. And I'm going to dedicate really most of my talk to explaining what these are, culminating with a more abstract view. But let me start with a bit of motivation. I work on building proof-assistant infrastructure, definitional and proof mechanisms. And most of us who have used a proof assistant for formalization know how important it is to start off with the right foot when doing definitions. So we need to get the definition at the proper level of abstraction, and ideally in a hassle-free manner. Sometimes these two goals can be a bit antagonistic, but unless we get the definition at the proper level of abstraction that matches our intuition, we're going to struggle later on when doing the proofs and when doing the interesting bits, when developing the meta theory. So in this talk, I'm going to focus on a particular piece of infrastructure that I think it's very useful for many of the meta-theoretical results that we're developing at POPL, many of the syntactic translations and interpretations that the researchers are developing. And I'm going to focus on recursion principles for syntax with bindings. In other words, recursion principles that are aware of the bindings and respect the binding structure. They pay their respect to the binding structure. And the main character of this talk will be the syntax of the lambda calculus. So these are the only notations that I will kindly ask you to remember. So please stay with me on this slide. So the lambda calculus syntax is specified by this grammar. So we have the lambda terms. I will just refer to them as terms. And the grammar says that a term is either a variable, or rather an injection of a variable, or an application of two terms, or a lambda abstraction of a variable in a term. You can see the more familiar notation there, but I'm going to use this more pedantic notation. I'm going to use these operators VR, AP, and LM. So terms, and this is very important, and this is people working on syntax with bindings know that this is sort of the source of all major difficulties. Terms are equated or identified modulo alpha equivalents. So essentially the bound variables do not affect the identity of a term. So for example, lambda xx is the same as lambda yy, which effectively means that lambda is not a free constructor. Okay, a brief parenthesis here. So I'm going to focus on the nominal approach. And one of the things that I like about this approach is that it does not start by encoding away, by correcting the informal definitions, but rather goes along with this informal definition and tries to make sense of them. So we have the lambda constructor is an actual operator that takes explicitly a variable and a term and returns the abstracted term. And a prominent variant of the nominal approach is nominal logic by Gaba and Pitts. But there are other mainstream approaches as well. So just to put them here briefly for comparison, there is the nameless or the Brown approach, where the bound variables do not exist, but a fixed position is being bound. And then we have the higher order abstract syntax approach that borrows the bindings from the meta level. So the way that these representations proceed actually has deep consequences in terms of the reasoning principles. I'm going to focus, as I said, on nominal recursion principles. Recursion principles for syntax with bindings within the nominal approach. Now, let me get a little more pedantic about terms. So these are the terms that I introduced before, the lambda terms. And we have this lambda that is not a free constructor. What does it mean? What does it really mean that they are equated modulo alpha equivalents? Well, what really happens is that we have the preterms, and
I'm going to just use P for the operators on the preterms. These are completely, sometimes they are called raw terms. These are a completely free data type, nothing special about it. And they have term-like constructors. And we define alpha equivalents inductively. And then we take the terms to be the quotient of preterms. And then we show that the preterm constructors are compatible with alpha, which allows us to lift the preterm constructor to term constructors. And after we have enough properties proved over terms, we can completely forget about preterms and focus on the terms. So we can work at that abstraction level. Now, this may look a bit tedious, but this is perfectly standard and fully automatable. These are polytypic constructions. So, and they have been automated in definitional packages such as Isabelle nominal. So this is perfectly standard and can be fully automated. OK, so let's delve into what a nominal recursor is. So let's consider this Knox operator that takes a term and a variable and returns the number of free occurrences of that variable in the term. For example, so you see here that term that on the left, how many times does x occur free in it? It's just once, because the left-hand side occurrence is free, whereas the others are bound. So this is what we want to define. So how would we define this in an ideal world, on which, incidentally, we don't live in? Please take 3 seconds of my talk to think about how you would define this. Well, we would write the expected recursive clauses, right? So we just want to traverse the terms recursively, and we show essentially how our function interacts with the constructors. In particular, in the lambda case, we're going to see if our variable is exactly the abstracted variable. And if this is the case, then there's no occurrence. So the number of occurrences is 0. Otherwise, we just export all the occurrences. Okay, so this is what we would normally write. And this is what, for example, Barendrecht in his monograph writes when he defines such operators, even though terms are equated modulo alpha equivalents. So we have a bit of a struggle between the intuition and reason here, trying to reach consensus, because this feels right. This feels like what we want. But on the other hand, if we are pedantic, and we should be when we formalize, the choice of the variable x may influence the definition. So we are not sure that this choice is completely irrelevant. But the intuition still says, well, it feels irrelevant. It feels like this is still the right definition. But this is not trivial. For example, that particular choice of the variable x in the lambda case, when we consider the abstraction, that is explicitly tested for equality with the variable y. So it is not absolutely trivial that the choice of the variable does not matter. And this is where nominal recursion comes in. And it essentially bridges intuition with reason. But it is not a Deux ex machina situation. So it does not just say, OK, this is actually fine. But it says that this can be completed to a definition. And the essence of nominal recursors is in this completion process. So what does it mean to complete this into a rigorous definition? For example, one of the nominal recursors, the most famous one by Gaba and Pitts, considers an extra operator to prop recursion, to further help recursion. So it's not only about the interaction with the constructors, but also about interaction with other operators. In this case, the permutation operator that permutes all the variables in a term according to some function. So if we consider these additional operators and verify some conditions, more about this a bit later, then we are fine. So then this is accepted as a definition. So we get our original definition as a subset of this fully rigorous definition, so to speak. So we don't have to change a representation or to recurse over different constructors. OK, so let's look at the situation a little bit more abstractly. So let's say we have, first let's look at a completely free data type, the data type of preterms. These are not yet quotiented to alpha equivalents. So let's say that we want to define a function h from preterms to some domain, some target domain A. Now, how the normal recursive definition goes through, essentially how I sketched before. So we're going to ask these questions. How does our intended function structurally interact with the constructors? So we ask what I will call the constructor questions. Now, how do we answer the constructor questions? Well, we need to put some recursive expressions there, but the way to conceptualize this more rigorously is to think that we have operators on the target domain that match the constructors of terms. So these are, I'm going to refer to this as term-like, as constructor-like operators. So we just plug those in as answers. So the answer would just say, well, our function is supposed to commute with the constructors. Okay. So what this really means is that we organize the target domain into a pre-term-like model. So we define operators that have the same arities as the constructors. And this is all. So this, for a free data type, we have this definition guaranteed to be correct by the standard recursion theorem for free data types. Now, moving from pre-terms to terms, we ask the same question. We ask the constructor questions. And the first step goes in the same way. So we know what we want to define. So we know how to answer these constructor questions, which means defining operators, constructor-like operators on the target domain. But in order to make this work, we are asking additional operator questions. Like, for example, here, we are asking, how does this intended function interact with permutation? And how does it interact with freshness? Here, we can treat freshness as a predicate. So these are two additional questions that help us that help us get a definition through. So we answer this by thinking about how our hypothetical function, how it is supposed to interact with these operators. And this gives corresponding operators on the target domain. And we have, only now we can have a definition, the definition accepted. So we need additional operators, and we need to check some additional properties. And now nominal recursion guarantees that there exists a unique function satisfying what we normally identify as the inductive, as the recursive clauses, which are 1, 3, together with some bonus properties that forced us to think in advance, essentially, about what we want. So this is really not a waste of time helping this definition go through, because we are talking about some properties that we're going to ask ourselves anyway when we are studying this function. Okay, so just to summarize how a nominal recursor works, we're asking, in addition to the operator questions, we're asking, in addition to the constructor question, we're asking some additional operator questions. And for the nominal recursors in the literature, they are all discussed in my paper. These operators, this combination of the operators vary. So we can have permutation, swapping, freshness, renaming, or substitution. And yeah, again, the questions that we ask about them tend to be the natural questions. And here is a piece of magic that I'm not going to justify, but in all the examples that I have seen in the wild, the properties are actually, the properties that need to be checked are often trivial, with a few exceptions. Okay, so let me skip to this other example, and let me just give an abstract view about what's happening here with nominal recursion. So this is a concept of an epi-recursor, which subsumes the nominal recursive example that I gave. So we have a base category and an extended B and an extended category, and we have this is, we can look at this diagram and not necessarily consider the rest. So we have this base category, which contains, corresponds to the usual notion of term or whatever syntactic binding we consider with their constructors. And we have the extension with additional operators that are specific to the specific recursors. And what happens above is that this is where we prop recursion. So we help recursion from above. When we want to define a function recursively from terms to some arbitrary set B, let's say, which is an object in the category B together with constructor-like operators, what we're doing is we get help from above, so to speak. So we extend this algebra, constructor algebra here to an operator algebra. And we use the initiality, which is the recursion theorem in this extended category. And we just take the restriction of this. So R is the forgetful functor that forgets the additional operators that were only used to prop recursion. OK. So some other things that you can find in my paper. Again, so I hijacked this for just giving a tutorial on nominal recursion. But essentially, I show how all the recursors from the literature are epi-recursors in the sense that I just described. And you can create new ones by cross-pollinating existing ones. And you have the an expressiveness hierarchy that discusses how the different operators fare relatively to each other. And I also studied the nominal co-recursor, which are in some sense dual to nominal recursor. In others, they are not. And I thank you for the attention, for your attention, and also I thank the people who have introduced the nominal recursor and co-recursors. We have the co-recursors at the bottom. All right. Thank you. Thank you.
Hi, thanks for the talk. The kind of naive question for type theorists when you see something like this is to think this is a special case of some sort of quotient inductive type or something like this. Yes. Is there any relation? Is this? I mean, I know that there has been quite some work on trying to find semantics or this kind of stuff for these kind of non-free inductive types. Is this related in some way?
Yeah, absolutely. This is related to quotient inductive types. And this is actually related to something that predates quotient inductive types, which are initial models in Horn theories. So you have a Horn theory given by conditional equations involving predicates as well. And you have some initiality theorems. Some of these recursors fall squarely under that pattern. But of course, I mean, they have their details. Because the alpha equivalency is defined in a specific way, is not defined so that one makes manifest that you are talking about a Horn theory. But other recursors, notably the original nominal recursor, is not in this category because it asks it has some non-equational axioms. So that would be interesting to see how that fits into the type theoretic framework, whether those types of non-equational axioms make sense there. But yeah, that's something interesting to look at.
Thank you.
Thank you. So you say that your aim is to combine recursors. Does it mean that you're aiming for some kind of category or two category of recursors so that you can make co-limits of them or something? Is that what you're...
that sounds like fun. But
like rough kind of fun, I would say.
But I'm not, yeah, so that would be an interesting sort of theoretical value to explore. So in my case, my motivation was what recursor to use for a definitional package in a proof assistant, and what are the relative advantages of different recursors. How they reduce to each other and so on. So to make the best of all worlds. So some recursors are more expressive than others. You will find this in my paper. But it's not only expressiveness. It's also some are lighter. Some require fewer operators. The infrastructure is sometimes lighter and so on. So there are different criteria there. And I think my conclusion is that I should have them all in a definitional package and reducible to each other. So I guess I could have reached this conclusion without studying.
Thanks.
Last question.
So related to what you just said, is it the best or the best so far? The co-recursor or recursor that you want to use, you want to use different combinations, but of course you studied the literature and this is where they come from, but you cannot exclude that somebody comes up with something even better.
Absolutely. So my friend and collaborator Dmitry, who asked the question, refers to a previous title of my paper, which was the world's best nominal recursor. But in the meantime, so I mean, the comparison is actually not even strict. So there is in this fauna of recursors, of connected recursors, there is room for improvement. So I don't have a maximality result of any kind. So it's even hard to say what it means for a recursor to be maximal, because this is something that I didn't get to discuss. You have different recursors, and they compare. This abstract view of recursors allows them to be compared with the expressiveness quite straightforwardly. So essentially, the closer a recursor keeps its extended category to its base category, the more expressive it is, roughly speaking. Because if you can move in an initial object preserving way between the extended categories, then you can simulate one recursor with the other. But I don't think there is a closest recursors there. So I don't think there is a most expressive recursor actually.
Thanks.
All right, so let's thank the speaker again. And before you all leave, I was just asked to forward a message from Philippa. The rooftop is open for the next.
mechanized proofs session. We have some exciting talks today. We start. I think I'm shouting loud enough. All right. Oh, of course. We're not just. Welcome to the mechanized proofs session. We have some exciting talks today. We start with mechanizing refinement types by Michael Borkowski. Please,
All right, thank you. Today I'll be presenting mechanizing refinement types, and this paper is joint work with Nikki Vazu from IMDIA and Ranjit Jala from UC San Diego. In case you're not aware of refinement types, we'll talk about these briefly, and this is a type system that can represent various sets of values. The domain will be a type in our underlying system, and these will be constrained by some kind of arbitrary predicate. These predicates or refinements are Boolean expressions. And the typical applications of refinement type systems are to prevent runtime errors at compile time, like array out of bounds, and to also be a lightweight verifier for functional correctness. The motivation of our project was that practical refinement types, the engineering of these, is gotten way ahead of the meta-theoretical foundations, and existing formalisms don't capture the essence of refinement types. The essential features of practical refinement systems that real systems show and we're interested in are both, first, semantic subtyping without writing casts so that the system can check subtyping obligations at function calls without the programmer having to write explicit casts, and parametric polymorphism as well. Now, existing calculi that have been published that have soundness proofs don't fully combine the essential features of practical refinement types. Some systems don't have polymorphism. For instance, Flanagan's 2006 system. Others don't have semantic subtyping and have syntactic subtyping, casts, or other replacements. For example, system FR, Sekiyama 2017. And Sekiyama 2017 also noted that some published systems have problematic meta theory that resulted from various workarounds. But in this paper, our contribution is to introduce a calculus. We call this lambda RF that combines semantic subtyping with parametric polymorphism. And we've also supplied for our meta theory 2 fully mechanized proofs, one in Coq and one in Liquid Haskell. Now, what makes these refinement types useful? We'll talk about our implementation of our system RF and these main features. Semantic subtyping is important because programmers want to avoid writing explicit casts. It makes the system much more useful. And the checks that arise for function calls, these can be turned into semantic checks and passed off automatically, for instance, to an SMT solver. And if we have polymorphism, then refinements can propagate throughout the system. Think of theorems for free, and that gives us a lot of benefit. So the outline for the rest of the talk, now that we've talked about the useful features of refinement type systems, we'll talk about 3 challenges that arose formalizing our meta theory, the solutions to each of these challenges, and then I'll talk about our mechanization and the lessons we learned there. So in brief, the 3 challenges are that when formalizing implicit semantic subtyping, we ran into circularities in the judgments of our system, and we'll talk about why it's important to avoid those. And we'll also talk about the challenges that arose in modeling our logical implications. And finally, with polymorphism, we'll talk about challenges around instantiating type variables soundly and how this arises in our kind of system. I'll provide a running example through this talk, and that will be if we implement arrays as functions. And so here, an array will simply be a function from a range of the natural numbers into whatever type is contained. And we have the new function, which will take some number n that'll parameterize this by how many indices are initially defined, an initial value. And so the new function that will create a function that models an array. There'll be a bounds check. It'll either return the default value or throw a runtime error if we try calling this code out of bounds. Now, the advantage of refinement type systems is that we can write a refined type for the get function that accesses elements of the array by calling the function underlying it. And we can prove at compile time that with valid code, the runtime error out of bounds is never thrown. And so for this, we have a precondition on the get function that the index we call at has to actually be in the valid range that's defined. So with that, we can take an array, for instance, consider an array of length 10. It doesn't particularly matter what value we put in there. And then we can see that a good line of code, get 10.4, will call index number 4, and that should be okay. Our system should be able to verify that that won't cause any trouble. And then a bad call to get, say, the 42nd index, that should be rejected at compile time. So now how do we know that we can actually verify this, what goes on? So when we call the get function with a valid index, that creates a subtyping obligation, because we'll have one refinement type in our system for our argument that might be pretty precise, and the function's parameter, the precondition, will require a different refinement type. So in other words, when we call it on 4, we know that 4 has the type of values that are equal to 4, and we need to know that this implies that the argument is between 0 and 10. So there's no exact syntactic way to handle this in our system, but this is a simple semantic obligation. So to give you a flavor of the judgments, we'll show part of the typing tree wherein we derive the type of get 10.4. And the way this works is that we start at the bottom of the tree and we work upwards. And so now we can use the function application rule. And then when we get to the type of an argument here, we use our subsumption rule to generate subtyping obligations. So this shows the subtyping that we have to check. And in our system, although the general system isn't syntax directed, the subtyping rules that will be used in checking code are syntax directed. And so we can unfold these subtyping judgments and generate semantic obligations or verification conditions. Here, for instance, checking the call reduces to checking the validity that for every v, if v is equal to 4, then v must be less than 10. And that can be handled automatically by an SMT solver. So the first challenge we come into here is that our subsumption rule, a new type is introduced on the bottom, and so we have to know it's well formed, that our refinements are actually valid Boolean program expressions, and so there has to be some kind of type checking. But if we use the actual type checking of our system, then we have this circularity that our typing judgment depends on the subtyping, which then in turn we have typing again and well-formedness, and then we get a circularity here. And now this doesn't necessarily preclude a proof for our system or another system, but it becomes much more complex. All of our theorems would be mutually recursive on subtyping, typing, and well-formedness, instead of the usual development where properties of simpler judgments like well-formedness can be proven independently, and that can help in the proof for lemmas like the substitution lemma for typing and subtyping. But another more serious circularity comes up when we formalize implication. So when we have an actual judgment that describes the implication of two refinements, then in terms of validating that these are well-formed refinements or defining our denotations, if we allow the typing judgment in here, we can actually get non-monotonic judgments in our system, and it could cease to be well-defined whatsoever. So because of that, it's important that we break the circularities. And so in our approach, we stratified our calculus into 2 layers. There's the full refined system, lambda RF, and we also have a unrefined lambda F, which is analogous to system F with features from our language. And lambda F type checking happens only with respect to unrefined base types, and that means we can check that our refinements are Boolean typed expressions without using the full lambda RF, and thus we break out of the circularity. And speaking of these implications, it's a challenge to encode implication in our system. Typical approaches to formalizing refinement types, when there are implications to encode, either an axiomatization is given, an SMT oracle is used, that's something that cannot be fully mechanized, or an approach like type denotations is used as well. That can be mechanized, but it can't be implemented because denotations are typically undecidable. For our approach, the direction we took was somewhat of a hybrid direction. We formalized exactly the properties that are needed of our refinement implication relationship. Then we were able to supply a mechanization of a denotations-based proof of the soundness of our implication. And we also were able to leave a neat interface where in the future we could encode other decidable implementations, for instance, trying to formalize an SMT solver. Our final challenge relates to the difficulty of polymorphism. The issue here is that when we have refined parametric polymorphic functions, a naive approach to instantiating our type variables can lead to losing contradictory refinements. And by losing contradictory refinements, if we lose information, our system can become unsound. Consider, for example, a refined type for the max function that just says the output is at least as large as both of the inputs. So what would we do if we tried to instantiate this function max on an argument that was a function type? The issue here is that our system doesn't directly support refinements of functions, so one choice would be that, well, let's not allow refinements on parametric polymorphic functions, but then we would lose expressiveness and have no ability to write this function here. Alternatively, whenever we instantiate by a function, we could just choose to drop the refinement because we can't compare functions, and the issue with that is that we can lose important information and lose soundness. Our approach here instead was to introduce a simple kind system that'll separate type variables into 2 classes, those that can be refined and those that can't. So we have a base kind and a star kind, and a base kind is used for type variables that can be instantiated by types with refinements. Those are our underlying base types, as well as existentials, and a star kind that includes all of the above, as well as the dependent function types, the polymorphic types, the things that we don't refine in our system. We then alter our syntax slightly to include explicit quantifiers in all of our parametric polymorphic functions. And so, for instance, here, max has an explicit quantifier that binds the type variable A to the domain of base kind. And finally, I'll tell you a bit about our mechanization. The goal of this was to prove both type safety and also the soundness of implication, which reduces to the soundness of the denotational semantics. We have details on these theorems in the paper. What this says is the standard type safety, that all well-typed terms continue stepping to a value, otherwise they don't get stuck. And the denotational soundness says that for every well-typed term, every valid interpretation, then that substitution, the interpretation of the expression, reduces to something in the denotation. Initially, we used liquid Haskell to mechanize our proof, and we defined the denotations, but that required negative occurrence in the inductive data type, And so, unfortunately, our proof was rejected the first time, but thanks to the help of the anonymous referees pointing this out, we were able to implement a positivity checker in liquid Haskell so that we could avoid this, since it turned out to be a source of unsoundness. So it's not possible currently to encode denotations in liquid Haskell, but we were able to mechanize these in Coq using the equations library. So we have two mechanizations. Liquid Haskell has type safety, Coq type safety, and denotations. And ultimately, we found that this was work worth doing. Liquid Haskell can scale up to large proofs, and we were able to patch a source of unsoundness with a positivity checker. The paper has more details on the implementation and the system. So in conclusion, we present to you our calculus lambda RF, and in the future, we'd be interested in extending this with the rest of the GHC primitives, such as data types, literals, and casts. Thank you.
Okay, thank you for what looks like a very interesting verification journey. Questions? Yes, please. Thank you for the talk. I have two questions. One is 2 slides back or so, you said that you used equations to work around an issue with the positivity checker. I don't really understand this. In which way those equations have something to do with the positivity checker?
The issue is that something like the denotations, also it comes up if you're trying to encode certain logical relations. These things, if they were formalized as an inductive data type, would require negative occurrences. In Coq, instead, you can define a fixed point that's prop valued. You lose decidability, and then the equations library, which was released in the last few years for Coq, helps with the non-structural termination requirements and the rewrites necessary to handle a proof of this size efficiently.
Okay, I see. Thank you. That makes a lot of sense. My second question is, can you go to your type of max? I don't really understand this, because you are quantifying over X of being type A, where A is some base type. But now A, I might very well instantiate it with a string or a tuple. And how does the inequality make sense on anything that is not a number type?
Currently, our calculus has Booleans and integers as base types. We've defined the comparison relation on Booleans. But to expand to things like strings that are not or something that's not necessarily comparable, we would need type classes instead of kinds. And so first, we have to formalize data types in order to be able to do something like type classes.
Okay, so the type of max would become more involved if you would have a more expansive type system. So then it would become like in Haskell, where you have something like for all A of type B, A of type B with ORT A to something or so.
Right. Yeah, that's the direction we'd like to go in the future.
Okay, makes also sense. Thanks.
All right, thank you. So we have a question from Discord. Breaking circularity. Can the subtyping judgment be reformulated to assume that its inputs are well formed instead of checking it in the premises?
In the subtyping judgment, we do make the proof more efficient by assuming that the types here are well formed. That kind of check doesn't happen in the subtyping judgment, but rather it's in the subsumption rule that the type we need, for the new type being introduced, we need to know the well-formedness here. And for this circularity, it's not directly in the well-formedness. We can assume the refinements are well-formed, but to fully formalize implications, our approach of denotations required some kind of quantification over, in the denotations, you have some kind of quantification over terms that have a specific type, and then quantifying over the typing judgment would be a negative occurrence. And so this breaking circularities was also motivated by our desire to formalize the denotations.
Okay, a very quick yes, no, or maybe question.
Okay, I only have a why question. Sorry. So I was just wondering why system FR does not requires coercions, according to in your terminology.
Why system FR doesn't require?
Why does it require coercions? That's what you pointed out as one difference.
For system FR, I believe the subtyping relation was semantics. So
Yes.
there's limits on the kinds of subtyping that can be expressed. In particular, our function subtyping rule has covariant and contravariant parts, so we can express a subtyping relation in the function domain. So my current understanding of system FR was that the subtyping relation might not quite be that versatile because it's syntax based.
It's a set of terms, but anyway, it has contravariance.
Mm-hmm.
All right, thank you. Let's thank the speaker again. Okay, our next speaker is Jae-Jin Kim. He will talk about VSTA, a foundationally sound annotation verifier. Please.
Okay. Hello, can you hear me? So hi everyone, this is Jianxin. I'm going to talk about our work, VSTA, a foundationally sound annotation verifier. So as you may know, annotation-based verifiers, a famous example is Daphne. In these verifiers, users will write annotations with the source code of the program to define the specifications and guide the verifier to complete the verification. And another type of verifiers, which is interactive verifiers, an example is VST, which verifies C programs with respect to the computer semantics based on the separation logic. In VST and other interactive verifiers, the source code of the program is usually separated from the specification and the proof of program. So if we compare these two verifiers, we can see that annotation verifiers are generally more automated and convenient to users. And they have a more consistent workflow since users can focus on the source code. Interactive verifiers, on the other hand, require more expertise compared to annotation verifiers. But usually they will have richer assertion languages and the form of proof of soundness. Annotation verifiers are usually first order, and users need to trust some implementations of the verifier, which is less reliable. So what we are doing here is we are trying to bring the benefits of annotated programs to the interactive verifiers. Now I'm going to show an example of demonstrating VST's workflow. So this is source code of a linked list reversal in C with annotations of specifications and assertions. So first, VSTA will parse the program to this control flow graph. We can see here the require is the precondition, and the ensure is the post condition. And the assert represents an intermediate state of the program in separation logic. Given this control flow graph, VSTA will find all the paths starting with the precondition or an assertion and ending with the post condition or an assertion. So there will be totally 4 paths for this function. The first path is from the precondition to the assertion. The second path is from the assertion going through the loop to the assertion itself. And the third path is from the assertion to the post condition, which exits the loop. And the last path is from the precondition directly to the post condition without executing this loop. So this is the 4 paths VSTA will generate. The user will need to prove these 4 paths, actually 4 hot triples. And these 4 hot triples, if proved, we will be able to derive the original hot triple of the function that's verify this function. One benefit of this control flow splitting is that if the program is modified or updated, only the proof of affected paths need to be updated. While in typical interactive provers, the whole proof have to be updated. For example, the loop body here will only affect the 2 paths related to the loop. And the post condition will only affect the two paths exiting the program. This benefit is more obvious in larger programs. And another prominent feature of VSTA is that it supports non-structural proofs. Structural proofs, which usually using current interactive verifiers, they follow the syntax tree of the program. This is because the goal-directed and tactic level automation is very difficult to go beyond the original horological rules, which are mostly syntax theoretic. And non-structural proofs, on the other hand, they do not have to strictly follow the syntax tree. In some cases, this can be a considerable convenience for the users. The first example here of non-structural proof is generalized looping variants. In horologic, looping variants are at a fixed location in the loop, usually at the start of the loop. VSTA relaxes this restriction by allowing variants to be actually anywhere in the loop, as long as there's no assertion-free loops in the control flow. In fact, the linked list reversal example shown before uses a generalized looping variant. The invariant is placed after the test of loop condition rather than before the test of loop condition. Though in this example, the generalized looping variants do not have an obvious advantage over traditional looping variants. So we can see this example here. This is a program to enumerate a matrix, which is a nested loop. Typically here, we need two looping variants in the verification because there are two loops. But if we look at the control flow graph here, actually we can find that only one of them, the invariant is enough. That is the invariant of the inner loop. There's already no assertion-free loop in the control flow if we add the invariant of the inner loop. And this invariant is also sufficient to carry all the information needed. In fact, the outer invariant can be inferred from the inner invariant. We also have an example in our paper showing that the general loop invariant can be more intuitive than loop invariants at the start. That is the operation of red-black trees. The second example of non-structural proof is the omitting join conditions. Like the program on the right, a join condition is needed in horologic if the control flow is joined. Like here, the loop can be exited normally or with break. So here we will need a join condition in horologic. But in some cases, it is more convenient to just follow the control flow of the program and treat them as separate paths. Like in VSTA, we can omit this join condition. This also applies to if branches. Notice that users can still write join condition if they think it's necessary. In summary, we propose a control flow splitting algorithm to generate subgoals from an annotated program. Our approach has three main benefits. The first one is flexibility. Our algorithm is based on the control flow graph rather than the syntax theoretic horologic rules. This allows more flexibility than applying horologically directly. The second benefit is less proof effort. The subgoals we generated are Hall triples that only contain the single path of execution. We call that straight-line Hall triples. These kind of Hall triples are much easier to prove, and the proof is easier to automate and update if the program is changed. The third point is soundness. Our algorithm is proved to be sound with respect to VST's program logic in C. We're able to prove the functional correctness of the program in original VST. After introducing the features of VSTA, we move on to the implementation details. The core of VSTA is the split function that reduces the functional correctness of a whole program to straight-line Hall triples. There will be four types of paths in the final results obsolete. The assertion-free path, which directly goes from the precondition to the postcondition without going through any internal assertions. And the head path going from precondition to an internal assertion. The tail path going from the internal assertion to the postcondition, and the full path going between the two internal assertions. The type of split result is shown on the left. The normal, break, and continue in the type means the path is ended normally or with break, continue, or return statement. We don't show the detailed algorithm here. Basically, split is implemented through recursion on the annotated syntax tree. An example here shows that the full path of sequential composition is the union of full paths in both statements and the concatenation of head paths in the first statement and tail paths in the second statement. So with this implementation of split, we prove that the split function is sound. Here's the soundness theorem proof, which basically means the splitted straight-line Hall triples can imply the original Hall triple. This theorem is proved by induction over the annotated syntax tree. We'll show the main idea for proof in following slides. It's worth mentioning here that before the soundness proof, that VST supports inversion lemmas. So it's kind of inversion of horological rules. We show the inversion of sequential composition and if branching here. Inversion lemmas are provable in VST because VST support both deep embedded horologic and high order assertions. Means we can quantify assertions in the assertions. The inversion lemmas are important in the soundness of control flow splitting. Now we'll use the induction step of sequential composition as an example to show our main idea of the proof. In this step, we are going to derive the original whole triple, PC1C2Q, from the split path on the right. So first, we can apply the sequential rule to our goal. The sequential rule requires an intermediate assertion R, such that PC1R and RC2Q. Then we can apply the induction hypothesis. Now we need to find R such that the remaining paths across C1 and C2 are provable. Then we can apply the inversion lemma on the assumptions. In that case, we'll find an appropriate R, which is the conjunction of the weakest preconditions of the following paths. So the proof shown before still remains an important point that worth discussing. If we look at the last step, we'll notice that we need the conjunction rule to complete the soundness proof of sequential compositions. And this is not caused by a proof strategy. In our paper, we give a counterexample showing that the control flow splitting will actually be unsound when the conjunction rule is inadmissible. Though the conjunction rule is provable in traditional horological separation logic, it is not compatible with some extensions like ghost updates, which usually use in concurrent verification. That's because the verification of the same program can apply different ghost updates that may be conflicting. So in current state, we don't support ghost updates in VSTA. Another problem related with the conjunction rule is the function calls. Also, calling functions with arbitrary specifications can break the conjunction rule. The reason is similar. The logical variables of specification can have different instantiations in the proof of the same program. We can see this function foo as an example. Here, f is the predicate dependent on the logical variable q, which describing a frame that actually foo doesn't exist. So it's possible to find such f that for two different instantiations of q, the specification is conflicting. So in VSTA, we additionally require all the Corley function specification to be precise with respect to this definition. Basically means we are able to unify the two instantiations and preserve the conjunction rule after the call. Traditionally, preciseness is defined on the predicates like here, while the precise function specification here defined on an operation. In fact, our precise function specification includes some common use cases of precise predicates like the resource invariance of logs. The definition of precise function specification is also more general than precise predicates in terms of function calls. We believe that most of C functions have specifications that are naturally precise. Non-precise specifications are usually caused by separation logic conjuncts that describe inaccessible memory slices to the function, such as the frame 4 here. Frame f here in the function 4. And these frames can be removed using the frame rule, like this. It can be removed using frame rule. What's more, the proof of preciseness can be efficiently automated. In fact, all the functions in our evaluation are proved to be precise using our automatic tactics. We can show some screenshots of our artifact here. You can see that they are both one line of tactical proof. Finally, we'll show our evaluations comparing the proof effort of VST and VSTA. The verified program are in these categories. First, we have some basic arithmetics and operations. Then we have 3 data structures, single linked list, double linked list, and binary search trees. Then we have a slightly larger program, which is a small step style interpreter for a simple imperative language. We can see that for the lines of code metrics, VSTA is generally similar to VST. In some examples, we are significantly better because we can achieve better automation on straight-line whole triples. And another benefit that is not obvious in the lines of code is the difficulty of the proof. Given the automatic tactics in VST is already very powerful, we still need a complex structured proof involve dozens of tactics. But in VSTA, for most of the time, you just need to apply full symbolic execution repeatedly, which is much easier than VST. In the future, we can improve VSTA in those directions. We can have better solutions for the conjunction rule. Like we can add annotations for the ghost updates, which allow user to explicitly write ghost commands in the source code in some way. That's we will not have two conflicting ghost updates. And also we can have annotations for function calls. Basically, users can explicitly instantiate logical variables. That's the conjunction rule will be trivial for the function calls. And another improvement can be partial assertions, which users can write partial state about programming instead of full state program, and we can apply the frame rule for them. So thanks for your attention. And
Thank you. We can take questions.
Thank you for very nice work. I was wondering, so there was something peculiar about the control flow graph splitting you showed in the beginning, where some code showed up multiple times in the splitting, like the part after the loop, if I saw it correctly.
Yes.
Is that related to the trouble with the conjunction rule? And like, is that really what actual automated verification tools will do? Because it sounds like you are then duplicating work by verifying the same code twice.
Yes, it is exactly corresponding to the omitting join conditions like here. So if users do not write join conditions, then for soundness, we have to repeat them like in the verification. So if users provide a join condition somewhere, then the following path will not be duplicated.
And if there were join conditions everywhere, would the conjunction trouble disappear?
Yes, but we do not take advantage of that in our proof. Yeah. So if there's only a single path, then yeah, the conjunction rule is definitely like provable.
Okay, interesting. Might have more questions later. Thanks.
Hey, hi, I'm here.
Oh,
hey,
yeah.
hi. Thank you very much for the talk. If so you're reducing all of this to single paths.
Yes.
Doesn't that risk having a combinatorial explosion in the number of paths?
Yes, this depends on and repeatedly on the join conditions. Basically, if users write less annotations, and we will generate more things in the split results. So yes, if you don't want the paths to be duplicated, you can write join conditions for them.
All right. Okay. So there's a user way around this.
Yes.
Okay. Excellent. Thank you.
Okay. More questions? There was a question over there.
Can you speculate at all about how you might support the frame inference?
Sorry.
Right
Oh,
sorry.
Can you speak that again?
Can you speculate at all about how you might support something like the frame inference? It seems like the idea of breaking down the verification condition up front before trying to solve anything makes it difficult to figure out what your state is going to look like.
I mean the partial assertion part.
Yeah.
We can support like notations for something you don't want to repeat for the following path, and that doesn't seem like it's like for the following assertions in the same scope, we automatically conjunct a frame for that, and for the following path splitting, that will exactly the same.
Thank you.
Hey, over here, yeah. So it seems that one of the benefits that you would get with this splitting is when you change parts of the code, you only have to redo the proofs for the CFG or the part that is affected by the code. So yes. Have you tried measuring how this would improve the performance in this interactive development?
We have some tables showing in our paper, which I don't present here in the presentation. Basically, it's slightly like as I show in this toy example here, this example. So there will be very small changes to the, like only the affected paths have to be updated. Yeah, they are actually in separate verification files. So yeah, so in engineering perspective, we can also speed up the verification time.
Okay. Are there more questions?
remark, the absolute program is wrong.
Sorry?
Okay.
Come back. Once again. No.
Absolute
value program.
Oh, that's the first.
It's right.
Yeah. It's wrong.
Because you do X is minute and it doesn't work. There was an error in the Java library, so you are not the only one.
I don't see where it's wrong.
Yeah, this is probably a typo on the slide, so it's a problem with generating slide code. All right. Okay. Thank you very much for the. We will take other questions offline. Thank you. Okay, so moving on to the next talk. This will be by Yuting Wang, and this is on fully composable and adequate verified compilation with direct refinements between open modules.
What happened? Hello, can you hear me? Okay, I'm going to talk about verified compilation of open modules with direct refinement. It's a joint work with those people. So the state of art of verified compilation is, of course, COMSAT, which has many great applications. The idea is that if you have a C program, you compile it with COMSAT, you generate an assembling program, you can derive a refinement between the source and target semantics. This refinement is represented as a simulation between small step executions. In the original COMSAT, you can only support whole program semantics, which means you must enter from the main program and return from it. When we move to the open modules, then the entry point may be something other than the main functions. For example, in this figure, we enter from F. And you may also invoke external calls. So in this talk, I'm going to use the black arrows to represent the internal executions and the blue ones to represent the external executions. And in this case, at the different language levels, the program states you will have a specific language states. For example, at C level, you have function calls. At the target level, you have register states. And also, the memory state is exposed. So you need some kind of, this refinement will need some kind of environment to relate to those states. And we want this refinement to directly relate the source C and the target assembling states without having the user to know how the compiler is implemented. But this is not the case for the existing work. In the compositional COMSAT, you have a single refinement which uses the C interface, which basically means the assembling semantic is distorted. It needs to interact through the C function calls. And in COMSAT M, the refinement is a union of refinement which is derived from the compiler passes. And in COMSAT O is a concatenation of refinements. So basically, if the user wants to use this kind of refinement, to a certain extent, he has to know how the compiler is actually implemented. So what is the difficulty? The main difficulty is the compiler has like several passes. If you approve the refinement for the individual passes, how can you actually vertically compose them in an open module setting? So basically, how can you hide those intermediate semantics? So we provide the answer to these questions by developing an approach to direct refinement that supports all the important features for compiling open modules, including vertical and horizontal composition and the equivalence between the semantic and syntactic linking, meaning there's no distortion of the semantics. This is also known as the adequacy property. We also support the heterogeneous modules with free calls between them. And this approach is applied to the full compilation chain of COMSAT starting from C-Lite. So we believe this first version supports direct refinement. And there's also extension to user level verification, meaning you can have a direct refinement from a high level user specification all the way to the assembling programs. And in this work, we basically focus on first-order languages with global memory and pointers. So let's take a look at a running example. And this example consists of two modules, a client and a server. So the client will accept requests for encryptions, and you will forward those requests to the server. So a typical interaction is environment initiate a request. For example, it wants to encrypt the value 11. And then the client calls the server, calls the encrypt function by passing this value. It also passes a callback function called RCD to the server. And the server performs encryption by XORing the value with a secret key, which is 42. And it stores on the stack frame of the server at the address RSP plus 8. And then it passes this pointer back to the client. And then client will read from this pointer, read this result, and store it in a global variable. So why this program is interesting, because it actually have non-trivial like ping-pongs between two different modules, and also passing of pointers between the client and the servers. So you have like a leak of pointers, memories. And so intuitively, this should be verified in 3 steps. First is that you prove the concept is correct. Then from this direct refinement, it guarantees the refinement for the client. For the handwritten server, we need to design a specification and also show this specification refines the implementation through the same direct refinement. And then by vertical and horizontal compensation, we can propagate this refinement all the way to the link to the target program. So I'm going to talk about this in reverse order. I'm going to first talk about the second and third step, and then finally the first step, because the first step is the most difficult one. So first, let's take a look at what this direct refinement is and how it guarantees the adequacy and horizontal computation. So the direct refinement between scene and assembly is basically a forward simulation with 2 ingredients. One is the invariant between the source and target program states. For example, the source C function calls, it should be mapped to the register and the memory state according to COMSAT's C calling convention. There's also a single injection from the source memory to the target memory. The second is protection of the program states across the external calls, which basically means that if you perform external calls, the external call cannot modify the private state of the system, so that when the external call returns, the simulations can resume. And the adequacy is trivially guaranteed in this case because, as we just discussed, it just directly reads C and the assembly state, so there's no distortion of the semantics. The semantic linking and syntactic linking is just the same. Second is a horizontal computation of direct refinements. This is guaranteed by the what is called the direct protection of the private states. For example, it requires the callee saved register and the stack pointers is not modified or restored when the external call returns. It also enforces a certain form of memory protection, which we'll discuss very shortly. So this protection enables the classical relay guarantee reasoning, which means the simulation relies on the environment to provide a certain guarantee, and then in turn it will provide the guarantee to the caller. And if you have a symmetric relay and the guarantee conditions, then you can do the horizontal composition because they will cancel each other out. This is the case for the direct refinement in our setting. Okay. So those are some basic concepts, but the difficult part is how do you do the vertical composition of those direct refinements? And this relies on this notion of a transitive cryptical memory relation. Recall the challenge is that we have those individual refinements, how we can compose them into a single one. And this is basically, if you zoom in into 2 consecutive refinements, it basically means you need to compose the relay guarantee conditions into a single relay guarantee condition. How this can be done, let's first take a look at how this memory protection is performed. Basically, the memory protection is realized by this NGP relation. What it says is that at the external call, you take a snapshot of the caller's memory. And from this snapshot, you infer which are the private memory you want to protect. Then in the callee, you cannot modify those private memories. The private memory has 2 parts. They are those shaded areas. The first is the source memory that is not in the domain of the injection, which means it is dropped by the injection. And the second is the one that is out of reach from the target, from the injection in the target memory, which means it's not in the image of the injection. Let's take a look at the example. This is a snapshot of the memory with the same execution sequence we see before, just before the server calls back to the client through the RCD. And you have those shaded areas which are protected, which basically contains, for example, return address RA and the pointer that links back to the previous stack frame. And during the call to the client cannot modify those private memories. For example, you cannot secretly modify your return address. So when the client returns, it can safely resume the simulation. So how do we do the vertical composition? So in this case, we have these INGP relations. And the observation is that the INGP is actually, in its protection, it works for all the compiler passes. So you can basically replace all the relay guarantee conditions with INGP conceptually. And also, it's actually intransitive. So it means two parallel INGP, it can be composed into a single INGP. Okay. So in this way, you realize the hiding. The proof of a transitivity is actually quite non-trivial. The key step is at the external call point, and you want to pretend that you only have a single INGP relation. But so we start from a composition of two injections, and these injections get evolved throughout the external call. When we return from the external call, we want to go back to our actual implementation, which is this parallel refinements. So what we need to do is we need to split this evolved injection into two and construct an interpretive memory state. And this state must satisfy this INGP relation. So the problem is how we construct this. And previously, this problem was thought as very technical and difficult without relying on some kind of extensive changes to the verification framework. But what we find out, this is also the main technical contribution, is that this is actually an inherent property of INGP. So the idea is that the protection you get after you compose two refinements is stronger than the individual protection. So let's take a look at this example. So you have first injection represented by the solid red arrows, and the blue, and the second injection by these blue arrows. The top left blocks, it's actually not protected by the first injection because it's in the domain of the first injection. But it is protected after the composition because its target block is dropped by the second injection. And similarly, for the bottom left memory block, it is not protected by the second injection, but it is out of reach from the first injection. So after composition, this is protected. In the end, most of the memories are protected. The only one that is public and can be modified are the memories that is injected through from the source to the target by those two injections. So to construct this M2 prime, the idea is very simple. You basically copy all the protected memories over, and then you project the updated public memory from the source. And this respects the parallel INGP because we have just said the protection after the composition is actually stronger than all the individual compositions. So this is the key idea and the observations we made in this paper. By adopting this idea, we build a concept with the direct refinement. The left table shows the relay guarantee condition for the individual compiler passes. And the condition is basically has a form with an environment indexed by some protection. So if the protection is the INGP, then you compose two of the conditions. Those two INGPs will be merged into a single one. We also have a weaker protections for passes that doesn't need such strong protections. But in the end, everything will be absorbed into this INGP relation. And this is a naive concatenation of all the relay guarantee conditions of all composite passes. And by using the rewriting rules, we can finally rewrite it into this direct refinement. So the CA INGP basically says there's a direct connection between CA and assembling through this INGP relation. The RO is optimization. It enables optimization such as constant propagations. And you also have well-timed conditions, this WT relation. The last one is just always hold for the assembling program, so it's not significant. Okay, so So this is the work we have done. We basically developed a version of COMSAT with the direct refinement. So we actually show that the direct refinement for realistic verifiers, verified compilers are possible. The key discovery is that the creepy relation with memory protection is actually intransitive and applies for all the compiler passes. And I think this kind of a relations is actually quite general and can be applied to other compiler verification projects. So all the artifacts are online, and you can check it out. And let's also like ongoing future works by reducing this, connecting this direct refinement back to the whole program correctness of a COMSAT, and also connect with the user level program verification. And we are also experimenting with applying it to other first order language like Rust. That's it, and thanks for this.
Thank you. Thank you very much. Questions?
Hi, it's lovely to see this actually being done properly, but I always thought the problem was that logical relations don't compose, and here you're in a first order setting, right? So, I mean, does what you've done have anything to say about what would happen in a higher order language? Because I always thought that was where the real problem lay.
Yeah. That's a very good question. And yeah, basically we are working in the first order setting. So, but even in the first order setting, it is not so obvious those things are composable. So what the technique, like maybe some kind of theoretical insight is, with strong enough protections, those things just become homomorphisms, the invariants. So their homomorphisms are naturally composable. But when you move to the higher order setting, like of course logical relations are not like composable in general. So I'm not sure how much this, but there are also work on the proving transitivity of special cases of logical relations that have a similar flavor with this construction of interpreting state in this work. So maybe for those special cases, this technique will work. But in general, I think it's a very hard theoretical problem, and I don't know the right answer.
Thanks.
Thank you. More questions? Okay.
Hi. So this transitivity argument that you showed, it seems to involve some kind of separation argument between states. So would this suggests that maybe this might work nicely in a separation logic rather than a regular logic?
So in this case, I think we didn't actually employ any like a separation logic reasoning, but there are compiler passes in COMSAT that has built-in reasoning that based on separation logic. So I think in that case, the proof of those passes already taken care of those properties. So we just reuse the proof as it is. So basically in this technique reuse the most of the COMSAT proofs. The real problem is writing at the boundary of modules how you do those transitive compositions.
Okay. So you don't think there would be anything to gain here from using some kind of separation logic for this argument?
I think if you want to extend it into other compiler passes, even in the whole program setting, you need some kind of a separation logic. But the proof seems to just work in this open setting as well. So that's my guess.
Okay, thank you.
Okay, more questions?
Maybe this is the same question again, and maybe you said this and I missed it, but could you spell out the assumption on the footprint of the assembly versus the C that you have here?
Oh, this one?
Well, in general, what are you assuming about the assembly?
So I get what it is. So basically, we follow. So this work is based on the COMSAT. The approach is that even if you are writing an assembling program, you have to give it some kind of specification in terms of label transition systems using the C interface. So this So this refinement between the server and the specification must interact at the C level. But internally, we don't care what this implementation is, but it has to act according to the C calling convention. Yeah. So that's why this compositions works. And I know that many people are interested in linking with arbitrary assembling programs. But in our case, if you don't get a kind of a C-level specifications, then the linking, you just cannot link. But I think this is also the difference between our work and the previous work. The previous work always try to do those two things together, like linking with arbitrary assembling program and proving the compiler correctness correct.
But you can, for example, pass in the address of some complicated C structure, and the assembly can walk that structure.
Yeah, if it is not protected by the C.
Thank you.
Yeah.
All right, thank you. Let's thank you, Ting, again. All right, the final speaker in this session is Josh Cohen, and he will talk about the formalization of core Y3 in Coq.
Hi everyone, I'm Josh, and this is joint work with Philip Johnson-Frey. So building deductive verifiers can be quite challenging. And by deductive verifier, I mean a program that takes as input a program annotated with some specification written in a program logic and produces as output a set of logical formulas that it will give to, say, an SMT solver. And these challenges really come from two different sources. There's the actual, the fact that you want to make sure that this formula is solvable efficiently by the SMT solver, which involves doing various heuristics and simplifications and so on. And there's the bigger problem, which is the gap between the source logic and the target logic, where you want to write a specification for your program in a nice, expressive source program logic, but SMT solvers support much simpler logics. So a better approach is to use an intermediate verification language, the two most well-known of which are Y3 and Boogie. And the idea here is that you have an intermediate tool, which is providing a higher-level interface to these solvers, and it is handling all of the translation to these lower-level formats like SMT. And it's doing various optimizations and so on. And so for the person who's writing a deductive verifier, they only have to compile their source level program logic to this intermediate logic. And if the intermediate logic is nice and expressive, as we'll see Y3's is, then there might not be such a big gap between these two logics, and the task will be significantly simpler. But how do we know that, I show here on the slide two examples for existing real-world deductive verifier toolchains, FRAMA-C, which uses Y3 as a backend, and Daphne, which uses Boogie as a backend. But how do we know that these kinds of toolchains are correct? The whole toolchain is doing this very complicated set of transformations from these rich specification logics to simpler SMT. It's spread across multiple different projects. Looking at hundreds of thousands to even millions of lines of code. And if there's problems and if there's bugs in any of these components, then that compromises soundness, where your tool says your program's verified, but in fact, there's a problem. And even if the tools individually themselves are correct, there can still be problems that can creep in at the boundaries if they make, say, different assumptions. But in fact, we can't even state a theorem that says that a toolchain is correct, because a lot of these components in here don't have formal descriptions. So there's an alternate approach to building these tools which addresses these issues called the foundational approach. And this is the approach taken by tools like VST, as we've seen, CakeML, and so on. And the idea here is you formalize the semantics of your program logic in a proof assistant, and you write down a program logic, in that same proof assistant, you prove the program logic sound against the semantics, and then you might even connect that to a verified compiler as well to go down to the assembly language level. And if the user wants to prove a program correct, they have to carry out the proofs interactively in the proof assistant in that program logic, maybe with some custom automation or tactics. And you end up with a theorem that says exactly what you're proving about your program, that it's guaranteed to hold according to these semantics. And the only thing you have to trust in this theorem is the proof assistant kernel itself, as well as your formalization of the source language semantics. And you get a typically very expressive logic from this. However, these tools are harder to build and they're harder to use. You can't take advantage of the variety of SMT solver-based automation and the advantages of this intermediate language-based pipeline. And for a user, they need to know how to use a proof assistant. They also need to know how to carry out these proofs in the program logic with this custom automation, which makes these tools inaccessible to non-experts. So what we'd like is to be able to combine these two approaches. In a similar way as we saw with the VST-A talk, we want to enable both automation and these foundational guarantees. It's not practical, as we've seen, to verify the entire toolchain all at once, but we believe that the crucial ingredient is to verify these intermediate verification languages. And we're looking specifically at Y3. And if we have a verified implementation of Y3, that is a verified compilation from Y3 formulas down to, say, SMT, then the problem of writing a verified deductive verifier is reduced to the problem of writing a verified source program logic to Y3 compilation. And as we'll see in a minute, this Y3 logic is quite expressive, which means, again, that this gap might not be so large and those proofs will not be nearly as difficult. And a verified implementation of, say, Y3 would help to do for foundational program verifiers what tools like Y3 and Boogie have done for verifiers in general, namely make it much easier to build front ends for a variety of languages because they're doing a lot of the hard work once and for all. But in order to do this, we need a formal semantics for Y3, which before our work did not exist and in full generality. And so with our work, we give such a formal semantics in Coq, and then we're going to show that it can be useful in developing a future verified version of Y3. I'll note that Boogie, which is a simpler logic that doesn't have a lot of the recursive structures that we're going to see in a moment, has been formalized, but until our work, Y3 had not. So what is Y3? I'm going to give just a brief amount of background here. It has two parts. It has a core logic, which is what we're concerned about, and I'll give more details about that in a minute, as well as an ML-like language built on top with annotations. And some tools that compile to Y3 will directly create terms and formulas in this core logic. Other tools will construct these YML programs. Y3 outputs to and supports about 20 different solvers in the back end, including SMT solvers, proof assistants for more difficult goals, as well as specialized solvers for, say, numerical goals. And the way that this works broadly is that the Y3 will translate these formulas via a series of transformations, which you can think of basically as functions from formulas to formulas. Depending on the exact set of features that a solver supports, the exact transformations will vary. But the idea is that a verified Y3 involves verifying the soundness of these transformations. Y3 is used in lots of verification tools. I show here just some of the more recent and notable ones. OK, so what is Y3's logic? What is the thing that we want to formalize? Well, we start with a classical first-order logic, add things like polymorphism, let and if expressions, and then the real difficulty comes from these recursive structures, where Y3 includes algebraic data types with pattern matching, as well as inductive predicates and recursive functions and predicates, all of which can be mutually recursive. And why does it include these features? Well, the goal is to be as expressive as possible while still allowing automation via translation to SMT solvers. And I'll note that this is broadly similar to the logic found in tools like Daphne and Verifast, also SMT-based, which suggests that this is a reasonable middle ground of the kind of features you want. So our semantics is a denotational one, which means that we interpret Y3 terms and formulas as objects in Coq's logic. Or in other words, we give a model of Y3 in Coq. And how this works, a slight simplification, is we start with a Coq function domain, which maps Y3 types to Coq types. And then under a given valuation, we can define the interpretation of terms and formulas. So a formula becomes interpreted as a Coq proposition, and a Y3 term of type tau will be evaluated as an element of type domain of tau, ignoring polymorphism for the moment. And the core first-order logic is encoded the way that we might expect, where a variable value, to evaluate a variable, we will simply look it up in the valuation. A Y3 and becomes a Coq and, a Y3 for all becomes a Coq for all, and so on. To deal with function and predicate symbols, things start getting a little bit more complicated, where now we have to deal with type substitutions and polymorphism. And to deal with the problem of well-typed function application, where we can have functions of arbitrarily many arguments of some unknown but specified types, we use a nice dependent data structure called heterogeneous lists. Now, as I mentioned before, the real challenge comes from all these recursive structures. And I wanted to highlight a few of the design decisions that we had to make, or that we made through the course of this. I won't be able to get into the details in many cases, but I encourage you to check out the paper if you're interested. So existing descriptions of this logic really specify these recursive structures by stating the conditions that they have to satisfy. So for instance, we might say for the interpretation of an algebraic data type, it has to be the case that the constructors are injective and disjoint and so on. And we want to go further than that. We give explicit constructions of these different objects that satisfy these properties. And to do this, we draw on a wide variety of ideas from classic PL theory. To encode our algebraic data types, we use W types. To encode inductive predicates, we use impredicative encoding. And to encode recursive functions, we use well-founded recursion on a specific predicate over these W types. But the idea is that this approach is highly layered, where the encodings get very, very complex, but a user of the semantics doesn't need to worry about any of that. They only need to know the higher level properties of these recursive structures. And I'll talk about a few examples in a little bit. We also encode things as generically as possible, where with only minor amounts of refactoring, we believe that our encodings of generic algebraic data types and inductive predicates are not unique to Y3 and could be reused in other similar developments. But it's worth noting that when we do things this way, where we give these explicit constructions, these structures interact with each other. And the interactions can get extremely subtle. So for instance, to define these recursive functions and to prove that everything terminates for Coq, we need to reason about the very, very precise interactions between these W-type encodings, the pattern matching, as well as the well-founded relation and the recursive function itself. But once we have all that, we can define completely what it means for Y3 formula to be valid in a given context, which means that it's true under every interpretation that's consistent with all of the previously defined definitions. And we can prove some meta-theorems about the logic, like the fact that it's consistent and the fact that consistent interpretations exist, which means that if I have a list of well-typed Y3 definitions, I can always construct the corresponding Coq object. And it means that we're not accidentally creating vacuous definitions in Y3. So as I mentioned before, the eventual goal of this is to have a verified Y3 implementation. And the way that this works, I show in this diagram at the bottom how Y3 is taking your input formula and applying a series of transformations to it before sending it to a final solver. And so to have a verified implementation, we'd want to show that each of these transformations is sound, either by verifying or by validating that the correctness for an individual input, and composing all of these proofs, perhaps along with a tool like SMT-Coq, which enables sound use of SMT solvers within Coq. And we could compose all those proofs together to have a complete verified implementation. And we wanted to show that our semantics would actually be useful for this purpose, in particular by taking two transformations from Y3 and proving them sound. So those two transformations are first the elimination of let bindings, which is a very simple transformation, and it's almost trivial to prove correct. However, it has quite an involved termination argument because it's not structurally recursive. As well as the axiomatization of inductive predicates, where each inductive predicate is replaced with axioms asserting that its constructors are true and the inversion principle holds. And this turns out to be a much more involved proof, relying on the least predicate properties of inductive predicates. However, the important thing is we don't need to reason about our complicated encoding. We only need to reason about those higher level properties in this proof. We also want to evaluate whether our semantics are correct. And as well as whether they're useful. So to do this, we built a proof system on top of the semantics. So we prove all of the familiar and classic natural deduction rules to be sound. And then we built a tactic library as well, where we proved tactics like induction over algebraic data types, unfolding recursive functions, simplifying pattern matches, and so on. And again, all of those proofs, which rely on all these structures, don't rely on the details of the encodings. They rely on the higher level interfaces. And we then use this to prove some lemmas from Y3's standard library about lists and trees to ensure that we can actually prove the types of goals we expect to be able to prove using these semantics. And I give an example here of the lemma that shows that if we have a binary tree and we do an in-order traversal and take the length of the resulting list, it's the same thing as just computing the size of the tree from the beginning. And the key idea here is that we can define all these tactics, we can prove them correct, we can prove these goals in the way that we expect, which gives us confidence that our semantics matches the intended ones and that we're defining these structures and giving the correct properties, well, correctly. So to wrap up, we gave a formal semantics in Coq for the logic fragment of Y3, which is this extension of first-order logic with polymorphism and these various recursive structures. In the future, we'd like to extend this work in a couple of directions. So we'd like to continue to verify these transformations to produce a verified Y3 implementation, perhaps, again, with a tool like SMT-Coq. We'd like to extend this to features of Y3 that we haven't yet included, like function types. And we'd like to use a tool like MetaCoq, which would enable us to prove Y3 goals foundationally in Coq, but have more idiomatic proof goals instead of with our deeply embedded proof system from the previous slide. And the key idea that I hope everyone takes away from this talk is that verifying these intermediate verification languages is useful. We have the tools to do it. And this can really, really help us to build these foundationally verified verification tools without sacrificing automation. All of our formalization and our proofs are available at that link here. Thank you all for listening. I'll now take questions.
Thank you very much. Questions? Thank you. In the beginning, you mentioned that you interpret types as Coq values. And there you say you want to do function types. So I'm curious, what is the plan?
I mean, so the Y3 types become Coq types, or really they're Coq sets, to be a little more precise. But I don't think that function types would cause significant problems there because everything is living in set. I don't think we have to deal with universe problems.
You want to map them to Coq function types?
Yes.
Okay. All right. Let's not neglect the online questions. So there's a question about the notion of Y3, assuming that all types are inhabited. Does this show up in your formalization? Does it affect the proof?
So we prove according to the typing. So we give it. I didn't talk about this in the talk. We formalize all of Y3's typing rules and give a verified type checker, and we prove that this implies that all Y3 types are inhabited. One of these syntactic Y3 checks is on termination, and on inhabitation, and we prove that that does correspond to the types being inhabited.
All right.
About termination, which you just mentioned accidentally. So how do users of Y3 specify these well-founded measures to indicate termination, and what consequences does this have for your tool?
So right now, the termination check in this formalization is based on structural inclusion of algebraic data types, and that's done automatically. The current Y3 implementation is a little bit more general, where it allows a lexicographic order over these structural inclusion, which is another thing that we plan to implement in the future. But there's no, in the core logic, there's no specification of measure or anything. It's just based on a structural inclusion.
Thanks.
Right.
So you mentioned early in the talk that there already was a formalization of Boogie, and then you concluded with a ambitious agenda to verify Y3 itself and also use a bunch of other bullet points, including MetaCoq. Has anything similar been done in Boogie or any other tool?
So there is, the work that I'm familiar with for Boogie is based on producing certificates to validate certain Boogie passes, and that's done in Isabelle. So I don't know if they get all the way to validating all of Boogie's passes, or they just take a few of the key ones. But yeah, that's
okay. Thank you. More questions? Let me quickly insert a question here about the reusability of your approach. You seem to have a lot of generic infrastructure. Do you consider organizing this into a framework for specifying semantics of logics and denotational semantics maybe in general?
Yeah, so that's something that we thought about. As I mentioned, that certain parts of the semantics we believe can be done fairly easily.
Quite a lot.
Yeah. So in particular, the algebraic data type encoding and the inductive predicate encoding, as well as other parts like our heterogeneous lists, where we sort of develop a generic library for that. So yeah, we have considered that as well. Yeah, but we designed things in a way that were supposed to be even overly generic, sort of with that in the back of our minds.
Yeah, nice. All right. If we don't have more questions, let's thank Josh again. And this concludes the session, so we're up for a break.
Guillou. Yes. Yeah. Thanks for the introduction. So I'll tell you in that talk a little bit about orthologic and why it can help with formal reasoning. So I know it's the very last session of the day. We're all a bit tired. So let me first describe you why you may want to be interested in orthologic, and so why now is a good time for our last burst of energy. So I'm sure we all agree that reasoning in propositional logic is generally useful for a wide variety of applications, program verifiers, proof assistants, compilers, type systems, optimization problems, many more. I'm sure you all have your favorite use case of deciding if a certain formula is true or not. But unfortunately, that's in general also a hard problem to solve. Typically, the validity problem for classical propositional logic is co-NP complete. So we tend to use heuristics, which are very useful in practice, but which are also limited because of their unpredictability. They may depend on your exact computing power, sometimes non-deterministic factors. In general, they offer you very few guarantees about what they can and can't solve in a certain amount of time you're ready to give them. So the question is, can we somehow design algorithms which are guaranteed to be efficient and always predictable with respect to some theory that is sound with respect to our basic theory, but also well characterized? An example of where we can do that is when we take the system F-type system and restrict its polymorphism to top level only to obtain decidable type inference. So for classical propositional logic, we could try to solve the problem inside inducionistic logic. It would certainly be sound, but in terms of efficiency, it's not better, because deciding the validity problem here is p-space complete. So we have another proposal, orthologic. So orthologic is a propositional logic with conjunction, disjunction, and negation, and its underlying structure, its Lindenbaum algebra, is that of ortholattices. So classical logic corresponds to Boolean algebra, the way that intuitionistic logic corresponds to Heyting algebra, and the way that orthologic corresponds to ortholattices. So what are ortholattices? Ortholattices are algebras, in fact, lattices, which satisfies a set of axioms that you can recognize, and they're duals. So you have the commutativity rule, associativity, idempotence, the laws about the constants 0 and 1, double negation elimination, the law of excluded middle, the Morgan's law, and the absorption law, which make the whole thing into a lattice. But crucially, it does not in general satisfy the full distributivity law. In fact, if you added distributivity to these laws, you would obtain a Boolean algebra. So the kind of problem we want to solve is this. Let's be given some statements that we know that we assume are holding. For example, this first formula here. Does this other formula at the bottom hold? So you can try to figure out in your head if it does hold in classical logic and if you need distributivity for it. It's not so easy to do by head, but actually, yes, it is true in orthologic. And hence, it's also true in classical logic. I could explain you why that follows. So now the question is orthologic as a theory an interesting one to solve problems? And can we decide such problems efficiently? So we argue that, yes, orthologic has good properties to solve problems, properties that are both algorithmic, proof theoretic, logical. It has a proof system, which admits a polynomial time proof search procedure. It has the interpolation property, as my colleague showed earlier this week at VMK. And not only is it decidable in polynomial time, it actually has a normalization algorithm, which when you give it a formula, will find the smallest formula that is equivalent to the input in at most quadratic time. Can we use those properties in some actual applications? So originally, orthologic was used by quantum physicists to describe some quantum phenomena, and more recently by philosophers to describe epistemic logic. And in computer science, we actually used orthologic in a program verifier called Stainless to simplify formula and normalize them with respect to the algorithm I just mentioned to improve the cache-hit ratio and to simplify formulas. Orthologic is also now a core part of the Lisa proof assistant because it is able to take into account automatically a wide variety of syntactically obvious transformations such as negation, normal form, commutativity, associativity. It makes proofs easier to write and shorter to store and check. But there are also a lot of other possible applications of orthologic that have not been really implemented yet. You could imagine having some type systems with disjunction, union, and negation, where orthologic, the decision procedure for orthologic would give you type inhabitation or efficient decisions for subtyping. Orthologic can be useful if you have refinement types or liquid types in your language, and here maybe the efficiency and reproducibility across machines and across versions of systems can be more important than classical completeness. If you have pattern matching, you can use negation to reason about the fact that a certain term is not of a given type. And at the end of this talk, I will show that we can actually use orthologic as a strict extension of data log. So what's new for today? First, we want to extend orthologic to support the use of axioms. Then we'll show some proof theoretic properties that this system has, mainly the cut elimination and subformula properties. From those two properties, we'll design a cubic time proof search algorithm with axioms. Then we'll show that there are classes of somewhat interesting formulas that have the same satisfiability in classical or logic and orthologic, including two-sat and Horn clauses. So that means that if we use our proof search algorithm for those, we actually find an answer that is also true classically. It has the same semantic. And finally, we'll extend orthologic with variable and predicate to obtain our little extension of data log. We have some additional results that I won't detail in this talk. So our proof system is sequence calculus based. We note sequence with formulas that are annotated on the left and right hand side, so that phi L psi R is intended to mean that phi is smaller than psi in all ortholattices. So it's a soundness, completeness kind of characterization. So there is a well-known classical sequence calculus, LK, which gives a proof system for classical logic. And it is known that if you restrict it so that every sequence is only allowed to have at most one formula on the right at any given point, you actually obtain a characterization of intuitionistic logic. And it turns out that similarly, if you restrict sequence to contain at most two formulas at any given point, but possibly two on the right, you obtain orthologic. So it's neither stronger nor weaker than intuitionistic logic. So here's a proof system we use. It's classical sequence calculus with the restriction I just mentioned. In particular, observe the cut rule, top left. And then we have an introduction rule for every symbol on both left and right hand side of sequence. And in the end, you have a rule to introduce axioms. That's in the title of this talk. Why are we interested in axioms? Because they make orthologic more expressive. You can reason given a certain body of knowledge of things that you assume or know to be true. In classical logic, that's not a very interesting topic because you can simply add axioms to the left-hand side of your implications or your sequence, but you can't do that in orthologic. And the intuition is that because of this limitation on the number of formulas you can have in sequence, you can't add as many assumptions as you want left of a sequence. So you need to actually support orthologic the hard way, to support axioms the hard way. Set of axioms that may be interesting are typically some things that are proven by external theorem prover or SMT solver maybe. And the problem we want to solve is given a certain set of axioms that we assume to hold, does a certain other statement always hold? So the first property we need to prove is the cut elimination property. If a certain statement is provable, then it has a proof where the only formulas that are removed by instances of the cut rule are among axioms. So we don't remove anything that is not an axiom. Because the cut rule is the only rule that can remove formulas when read from top to bottom in a proof, we obtain a subformula property like in the classical case. If a certain sequence is provable, then it has a proof that only uses a subformula of the input. We now use those two properties to design a proof search algorithm. This proof function that takes a sequence gamma delta as input. And it's essentially a backward proof search procedure. So you find all the application of the rules that can somehow conclude with gamma delta, and you recursively solve the premises of those rules. Now, the key observation is that because sequences have only at most two formulas at any given point, and because of the subformula property, we know that this function will never be called on more than n squared different inputs. So if we memorize the intermediate results, we know that we'll never execute the function more than n squared time, whatever the original input is. Now, what is the complexity of one run of this function? It's dominated by the number of rule applications. This is actually a certain constant number, plus one application of the cut rule per different axioms that you could introduce as per the cut elimination property. So you obtain a final complexity result, which is n squared times the number of axioms. And under some conditions, you can actually obtain n squared. Now we would like to know if there are some interesting problems which orthologic solves exactly with respect to classical logic. And that's the case, for example, of Horn clauses. So if you have a set of Horn clauses, this set is satisfiable in classical logic if and only if it is satisfiable in orthologic. So they have the same meaning. This is also true for two sets, renamed Horn, extended Horn, Q-Horn, some others. Now finally, we want to extend propositional orthologic with predicate and variable symbol, a bit like effectively propositional orthologic, so no function, no quantifiers. And the kind of statement we can encode is, for example, a congruence relation. So you have first the axioms about the equivalence relation, reflexivity, symmetry, and transitivity, and then you can express an axiom for every other symbol in your language and every one of their arity, every place in their argument that will express the congruence property. And now we can observe that those are actually Horn clauses, so they have the same meaning, the same semantic in classical logic and orthologic. So can we solve those kind of problem in predicate orthologic? Yes, let the degree of A be the maximum number of different variables that appear in the set of axioms. Then we can decide if a certain sequence holds with respect to all the instantiation of this set of axioms in time at most exponential in the degree of A. For comparison, in the classical case, where the equivalent domain is effectively propositional logic, you would have an exponential more in your runtime as far as we know. So finally, we get to a little data log generalization. Data log is effectively propositional logic, so it has only variables and predicates, and formulas are restricted to be Horn clauses. And we know that orthologic is correct and exact for Horn clauses. That means that we can use orthologic with axioms as a strict extension of data log. For the sub-problem that are data log problems, it has actually the exact same semantic. It would solve it the same way as a data log engine. But you can extend and express more things with negation and disjunction. And while here you would not have a classical semantic for those disjunction and negation, you still have a logical semantic, not something based on control flow or execution. And moreover, the runtime needed to the complexity of solving such a program would be exponential, similar to base data log. So that's about it. We saw what is orthologic and how it can help with doing formal reasoning predictably and efficiently. We saw that orthologic with axiom admits a cubic time algorithm. We saw some theoretical property of orthologic and effectively propositional orthologic, which in the end led us to a generalization of data log. And I also explained some possible application of orthologic. And yeah, that's it. I'm happy to take questions.
Can you say a few words on the models of orthologics? Like, do you have Kripke models or anything?
So good question. Models are actually ortholattices, simply like the way for classical logic your models are Boolean algebras, right? So now you have questions about what happens if you try to get full first-order orthologic and what would be your models. In that case, we have some ideas, some things that have been published in the interpolation paper I mentioned, but not complete results about it. We haven't developed Kripke model for those, and it's a bit outside the scope of this approach here.
I understand the lattice model, but is there a way to read the formulas like in natural language, which like and as and or as, because we can't read them that way, I imagine, or we would get distributivity. So how do we understand them intuitively?
Well, a good question. I mean, same as in intuitionistic logic, right? Can you read negation as negation in intuitionistic logic?
Well, I can read
yes.
and or and implies because I got distributivity and I've got like
yeah,
here.
right.
Yeah. Another question. So, okay, so you're not giving me an answer that you can read them that way. is there an implication connective in the orthologic?
Good question. So you can define implication connectives in some ways. They would not get all the properties you expect from it. In some sense, you have well-defined and well-behaved negation, but not perfectly behaved implication. It's a bit the opposite of intuitionistic
Let me
logic.
ask my question a different way. Do you have a developed, because you use it, do you have a developed intuition where you can stare at formulas and you have a good intuition as to whether they're true or not?
Well, for example, I have some because of training. And it's not so obvious, right? But that's also the case with classical logic. You don't necessarily know. So here's the example we had at the beginning. So I can argue that you can do negation normal form. You can substitute. It has some good properties you expect from classical logic or for our logic. And so you actually can deduce that way that formulas are true. It does not jump to your eyes, but neither does it in classical logic, I guess.
Hi. I was just wondering, do you get other or interesting logics by generalizing this restriction of the number of formulas? So say you generalize and said at most 3 formulas or at most 4 formulas. Do these give you different logics?
That's very interesting. So you could do other things. You can get something dual to intuitionistic if you lock sequence to have only 1 formula on the left. I think that as soon as you have 3 formulas or more, you get classical logic, but I am not completely sure. I haven't showed it properly.
You said for classical logic they have heuristics. My 2 questions. Do these heuristics work for you, and do you have better ones?
Well, the idea is here you don't need heuristics, right? Because you can solve the problem exactly in quadratic time.
N cube with 100 axiom, it will be slow. Huh?
Well, that's a good point. So it would depend on which application, right? Maybe if you have a type system, you don't have hundreds of formulas. But for example, if your axioms have all of the form not of an inequality, but just a single formula that you know how to hold, actually the proof search is done in quadratic time, which is already better. And for some other classes of problems, for example, the unit propagation rule is admissible in orthologic. So if you have some even restricted subset of it, you can actually solve it in linear time, maybe. It would depend on your exact application. But we run some tests, not with axioms, but with the quadratic algorithm. And even like you can normalize formula with up to millions of connectives in instance. Sorry. For applications which were program verification and proof assistance, that was plenty sufficient.
Is there a link between orthologic and effect algebras, which are also close by autocomplement?
I don't know, actually. To be frank, I don't know the topic well enough to answer you on that.
So if you give yourself a formula that is not valid in orthologic, it produces some counterexample?
Yeah, so what you can do is try to normalize it and try to find like a witness, the smallest equivalent formula that is not true, and maybe that is not that is equivalent to your input. Then you can maybe solve it with an external SAT solver if that's what you want, and then you can even reuse it as an axiom for your next the next thing that you can solve. Yeah.
So you can do this kind of relaxation process where you add more axioms.
Yeah,
and
exactly.
recover the power of classical logic?
Yeah, exactly. Although that would not give you a quadratic time procedure, of course, because you may need to add a lot of axioms for all we know. But that would give you a complete decision procedure, yes, a bit like with SMT solver.
There was maybe a last question. I saw somebody raising it. No takers for a last question? Yeah.
So that's a follow-up question to Odette's. As you said that you would obtain a decision procedure for classical logic by essentially counterexample refinement loop, right?
Yeah.
But has it been tried?
Yes, actually. So I don't want to say that this is competitive. We had a competitive application, but in a proof assistant we did this, and we have actually a method to solve arbitrary propositional tautologies using this. What you do is it's very slightly different, but you normalize the formula, and then you make a decision on some literal, you split it, and you renormalize with respect to orthologic, and so on until you get either a proof or you can't destroy the formula anymore. And as far as I know, this is a little bit more efficient than not using orthologic. It requires less proof steps.
All right.
Thank you.
Thank you very much. So let's proceed with the next talk, which is about deciding asynchronous hyperproperties for recursive programs, presented by Christoph Horem.
Okay. I think this should work. Okay, thank you for the nice introduction. As mentioned, the title of the paper is Deciding Asynchronous Hyperproperties for Recursive Programs, and this is joint work with Jens Gutsfeld and Markus Müller-Alm. Okay, so in recent years, a number of security flaws have been discovered, both in hardware as well as software systems. And in order to prove the absence of such security flaws in future systems, formal methods are required. A number of security properties characterizing the absence of such security flaws belong to the class of so-called hyperproperties. In a nutshell, a hyperproperty is a property of a system that depends on the relationship between different of its executions. So most of the work in recent years on the verification of hyperproperties has focused on so-called synchronous hyperproperties as well as finite state models. And while this may be adequate for hardware systems, it's not for software systems, especially ones featuring recursion. Here, a combination of asynchronous hyperproperties and pushdown models is a better fit. So in order, and while there's been some research on both of these features individually, there hasn't been any research on the combination of the two. And in order to address this gap in our research, we introduced a new asynchronous hyperlogic and also developed the first pushdown model checking algorithm for asynchronous hyperlogics. But before we go into the details of our contributions, let's first recall the notions of hyperproperties and asynchronous hyperproperties first. So classically in model checking, one has been interested in so-called trace properties. A trace is just an infinite sequence of sets of atomic propositions that hold along an execution of a system. You can see some examples here. And then a trace property is a property that may or may not hold on a trace. For example, a state satisfying P must eventually be reached. It's a trace property, and these can be specified, for example, using classical temporal logics like LTL, using the formula finally P. And then using this formalization, we can check for each of these traces individually whether they satisfy the specification, and in this example, each of them do. A hyperproperty, on the other hand, depends on the relationship between different traces. So an example would be the first occurrence of P is after the same number of steps on all traces. These properties require different temporal logics for their specification, like hyper-LTL. And you can see the specification of this hyperproperty on the slide. So the main differences to LTL and hyper-LTL are that the basic building blocks of formulas are propositions indexed by trace variables. So this P pi1 expresses that the proposition P holds on pi1, and using different trace variables then allows us to compare different traces with one another. And additionally, we have quantifiers binding these trace variables that range over a set of traces. And so
hyperproperties on a more formal level are properties of sets of traces. Now, hyperproperties can also be characterized as synchronous or asynchronous. The intuition here is that is based on how we match different positions for comparisons when we evaluate a formula. In the example from the previous slide, this happens in a synchronous manner. So we count the steps on each trace. So we compare the first position with the first position, the second position with the second position, and so on. An example where this way of matching happens asynchronously is the number of occurrences of P is the same on all traces. One way to evaluate this hyperproperty would be to match the first P position on each trace with the first P position, the second P positions, and so on. And as you can see in this example, this way of matching is inherently asynchronous, and this makes this an asynchronous hyperproperty. So there has been some work on hyperlogics for the specification of asynchronous hyperproperties already. I picked out two examples here that are the main inspirations for our current work and that also highlight what is unsatisfactory about the current state of the art. So 3 years ago at POPL, my colleagues and I introduced the temporal fixed point calculus HMU. And while it captures asynchronous progress very nicely in general, its decidable fragments have some drawbacks like a high complexity or also issues with expressivity. Later, the logic stuttering hyper-LTL was introduced at LIX 2021. It captures only a subclass of HMU's hyperproperties, namely those where the asynchronicity can be described by stuttering. And while its decidable fragments have a nicer complexity, there are still issues with expressivity here. So to sum up, we have two main motivations for the current paper. First is that we think that the expressivity of decidable fragments of asynchronous hyperlogics can still be improved, and that is without affecting the complexity of finite state model checking. In order to address this, we introduce mumbling HMU in our paper, which is just a more expressive hyperlogic than stuttering hyper-LTL. Second, as mentioned on one of my earlier slides, all approaches to asynchronous hyperproperties that we are aware of use finite state models. So we consider pushdown models, which are able to model recursive programs much more precisely in our paper. So let me illustrate what is new about our logic mumbling HMU. So this slide is kind of full, but let's go through it together. So our logic is inspired by the logic stuttering hyper-LTL, but it has several additional features that are new. And I want to illustrate them with this example formula here. But before I go into the details of each feature, let me explain to you why this specification specifies this asynchronous hyperproperty. So the hyperproperty is, in observable positions, the traces of the system are indistinguishable with respect to a function f being in the call stack. So we have this formula here. It expresses that the function f is in the call stack on trace pi1. Then this part of the formula expresses that it is in the call stack on pi1 if and only if it is in the call stack on pi2. Then we have this next operator that advances each trace to the next observable position, and a fixed point that states that this happens repeatedly. Finally, we universally quantify over the trace variables to state that this happens for all pairs of traces of the system. So what are the features here that are in our logic but not in stuttering hyper-LTL? First, we have fixed points. These just generally give us expressivity compared to the usual LTL modalities that cannot, for example, express arbitrary omega regular properties. Then what's new is non-atomic tests. As you may have noticed, in hyper-LTL and also in stuttering hyper-LTL, the basic building blocks of formulas were atomic propositions tested on traces. Now here, we have these brackets in which we can write trace formulas to test for trace properties on traces, so that's new as well. In these non-atomic tests, we can use Carré-like modalities. In a nutshell, these modalities allow us to inspect the call return behavior of traces generated by pushdown systems specifically. Then we have a simpler jump mechanism called mumbling, which I will go into more detail about on the next slide. And finally, we allow different jump criteria for different traces. In this example, this means that the observable positions on trace pi1 may be characterized in a different manner than the observable positions on trace pi2. So what is stuttering and mumbling, and why is mumbling more simple? So let me explain using these examples. Stuttering is defined using a set of trace formulas, and the stuttering next operator always advances to the next position where one of these formulas takes a different value. Mumbling, on the other hand, is much more direct. It's defined only using a single trace formula, and it always advances to the next position where this formula holds. Now, this is not only more direct and simple, it's also more expressive. In one of the more technical results of our paper, we were able to show that mumbling is more expressive when only LTL formulas are used in the definition of jump criteria. And while we were also able to show that the difference vanishes if fixed points can be used freely, this is due to the power of fixed points rather than due to the power of stuttering, as the first result suggests. So for the rest of the talk, I want to talk to you about our approach to pushdown model checking. Now, this is an inherently difficult problem for hyperlogics. As many of you may be familiar with, the emptiness of intersection problem for pushdown automata is an undecidable problem. And since pushdown systems are basically pushdown automata and hyperlogics allow us to compare different executions of systems, a reduction often leads to undecidability. Thus, restrictions are needed here. In our paper, we introduced the notion of well-alignedness. It's a restriction that we crafted to be as lax as possible so we can analyze as many systems as possible precisely. This example on the slide here should illustrate to you what is still allowed under well-alignedness. So you can see two finite subtraces with observable positions, and the height of these lines in between indicates the stack level. Now, at first glance, these traces look quite dissimilar. For example, the first trace goes onto a stack level that the second trace never goes to, and the second trace has some returning procedure calls that are unmatched by the first trace. Still, these traces are well aligned, and why is that? Now, there's some stack actions that cannot be pre-calculated by our algorithms. These are marked with arrows here, and since these stack actions are the same, namely two pushes, the traces are well aligned. Our approach to pushdown model checking then is to use well-alignedness in a well-aligned next operator, which in addition to its usual semantics expresses that the next step along the traces is well-aligned. This has an advantage over, for example, a global analysis where we only consider well-aligned sets of traces, because we can, for example, express that a set of traces is well-aligned, or we can restrict certain requirements to only pairs of traces that are well-aligned. And our approach to model checking is then to check for violations of this criterion in every step. Okay, so now that time is running out, let's come to my conclusion. Here's a summary of our contributions again, and our ideas for future work include, for example, an implementation of our pushdown model checking algorithm, a generalization of jump criteria beyond stuttering and mumbling, as well as using well-alignedness for decidable pushdown model checking in other hyperlogics. I thank you for your attention.
So any questions?
In your example, you had always 2 tracers for pi1, for pi2. It's limited, or?
No, there's also different ways to quantify. You can also use existential quantifiers. Most of the interesting examples use multiple universal quantifiers. That's why I used them here. Maybe what's also noteworthy about this is that the complexity rises very quickly with the quantifier alternation. So in practical formulas, you only want to use maybe a single kind of quantifier.
Maybe just if I have only universal ones, but I have 3 properties, is there an interesting hyperproperty of that form? So pi1, pi2, pi3. You know any?
Actually, I'm not quite sure. I'm sure. So most of the examples where you have 2 universal quantifiers, they also already by transitivity go to the whole set, and I'm not quite sure what a 3rd universal quantifier would do there for you. The only example from the literature that has 3 quantifiers has different kinds of quantifiers, so I'm not sure there.
Other questions?
Just any kind of 3 quantifier property like transitivity or associativity, if you want to prove it for your program that computes a relation, that would be a hyperproperty with 3 quantifiers. If your system computes a relation and you want to say this relation is transitive, that would be a 3 hyperproperty with 3 universal quantifiers, I think.
Okay, I would have to think about this, but I guess this answers the question here.
Any other questions or answers? So maybe I can ask a question. You've presented well-alignedness. Is there any other restriction that you can combine with it to relax it?
Well, there's still some things you can do to relax it, but when you do, it becomes quite unnatural. So one of the things we require is that the stack level is the same on all positions, and you could theoretically still do an analysis when you have maybe a bound on how much the stacks are diverged on the observable positions. But if you do something like that, the restriction becomes quite unnatural, I think. And we used the most smooth, so to say, definition here that gives us that is not too restrictive, so to say.
Any other questions from the audience? Okay, I have a follow-up question on the implementation. Actually, have you experimented with benchmarks? How much does it scale? What's the kind of scale of the systems on which you have exercised it?
Actually, we haven't implemented our algorithm yet. That's why this point is in future work. Yeah. So we are aware for other hyperlogics that there are implementations, and it seems to scale a bit when you don't have quantifier alternations. And when you have your first quantifier alternation, you tend to have to use special techniques to handle those because the complexity becomes quite high. So already without quantifier alternations and finite state models, the problem is p-space complete, so the complexity is not that low.
I see. Okay. So I guess we can proceed with the next, if there's no other question. Okay, thank you very much. So the next speaker is Patrick Couzeau. Actually, I think, yes, let me help you. Yes. Let me get rid of the yes. Thank you. So a bit of computer science pub trivia. I think the first paper at POPL by Patrick Couzeau was in 1977, if I'm not mistaken. So even with the interval abstraction, it's a pretty big interval, right? It's a pretty impressive achievement to have a paper today. Yeah. So the title is Calculational Design of Incorrectness Transformational Program Logics by Abstract Interpretation. We should be almost ready.
Okay, guys. So I go to full screen. I don't remember where. View, full screen. No. You can touch what you want.
It's preview, so just go to view and the last item of the menu. Oh, there you go.
The mic. I need the mic. You are ready? Okay, you hear me? No. Okay, so so if you are a mathematician and work on the east coast of the US, and I ask you what is true, you say what is provable is true. Then you visit the west and you ask to Tarski or others, so Pravis, for example, on the east, what is true? He says what the model tells you is true, and poorly computer scientists go from east to west, and I think it's bad because we already have the model, and so we should go west to east from the model to proofs. And that's what I will do, and how you do it this way. First, you define the natural relational semantics, because I consider only transformational semantics input-output. You must be structural, otherwise it's not funny. You can use rules, and I will give you a fixed point. Okay. Then you define an abstraction, alpha, of the collecting semantics, which is the most precise hyper property that defines the theory of the logic that you want. And the theory is a set of true formula. When you have this, you calculate the theory in structural fixed point form by fixed point abstraction. Why fixed point form? Because when you have the fixed point form, Mr. Peter Axel showed how to get the rules. Okay, plus you have this fixed point induction, I will explain why. And I take two trivial examples, which is OR logic and incorrectness logic, and they are not even in the paper because they are too trivial. But for a talk, for a talk, it's not so bad to be trivial. Okay, so what is the general idea? I apply it. You take OR logic, you take the strongest postcondition of the collecting semantics, okay? Then you have no consequence rule, so you had an approximation with the consequence rule, okay, you got it. Then you over-approximate have an approximation of fixed point, as we will see, and then you use Axel correspondence and you get the OR logic. I will show. Then if you are under-approximating, you replace over by under, and you do exactly the same thing, which explains that their two systems are related. So let's do it. I start with this small language, which is classical. I don't handle this in my talk. I don't handle non-termination, so I have only states and an angelic semantics which says if you start in this state, you may reach this one. Then I have to formalize this, so I use judgment. The first one say, if you start in state X, sigma, you execute S, you might reach final state sigma prime. And to do that for the while, I have another rule which says, if I start in sigma, I make 0 or more iteration, I might terminate and reach sigma prime. So here are the rules. You see, for the while, if I am in state sigma, I do 0 iteration, I am in state sigma. No one disagree, okay? Then if you are in state sigma, the test is true, you execute the body, it may terminate, then you do n more iteration, then from sigma you can do n plus 1 iteration sigma prime. And if you can reach a state for which the test is true, false, excuse me, you have terminated. And so Mr. Axel, I will show you later, tell you this is the same as this fixed point, where you say you have the least fixed point that give you the relation between initial and n iteration, and then you don't terminate, you terminate here, and the relation say ID is just I am there, I stay there, and the next one say I do 1 iteration, and then I get n plus 1 iterations. We see why. Okay. And then we come to Mr. Axel. He says, if you have rules in some universe, the precondition must be finite because you have proofs. The postcondition is an element of the universe. And if P is empty, you say that it is an axiom. Then you have a deductive system, which is maybe infinitely many rules with a premise and a conclusion. And now these define a subset of the universe. How? The first thing is you consider the provable things, and the proof is a sequence of terms, so that any one is a conclusion of some rules, such that you have proof before the premise, and then you take the next term to be the conclusion. That's the classical stuff in math. You prove by doing little steps of induction. And he said also, it is the least fixed point of the consequence operator. And the consequence operator is this one for this rule. You have hypothesis X, and you derive all the possible conclusions that you can derive from X using any rule. And what is interesting is that if you have any fixed point with a set order, there is a deductive system so that this fixed point for this deductive system is this one, which means if I have a fixed point, I can express rules. That's why I was saying express the theory with rules, because applying this, I get the rules here. So for the logic, what we do, we start from the collecting semantics, which is the singleton of the strongest property of the semantics. Then I do an abstraction to get the semantics. It looks ridiculous, but here you have all hyper properties, so it's interesting. Then I have a transformer, which is pose right image. Then I have representation of a function by its graph. Then I introduce over or under approximation, and I am finished. I've got the logic. So the first abstraction was a Galois connection between hyper properties and properties, or trace properties. Sometimes you just take the union. So you take the union of all traces, and you have lost information. You, for example, you cannot no longer define dependencies and things like that. Then the post image is trivial. It's another Galois connection between a relation and a transformer, and it's just a post image. That is, you take all state in P and then apply the relation and look where you arrive. And the last isomorphism is you encode a function by a functional relation. That is, for each argument, you remember the value of the function for this argument. I cannot make more trivial. It's completely trivial. And so now we have a logic. I take the strongest postcondition logic to be the abstraction that we have defined. So for each precondition, it gives you the strongest postcondition. And you use some notation, which is not really interesting. And then I want to have this in fixed point form for my semantics. So I have this theorem, POPL-79, which says if you have a Galois connection between complete lattices, you have a concrete and an abstract function, and they commute, then the image of the least concrete fixed point is exactly the abstract fixed point. So to apply it, I say this is the semantics, this is the alpha that we have defined, and now I will have the theory of the logic in fixed point form. Then I apply Axel, and I am done or almost done. Okay, so I do it, and I get this. So for the while, you start with P, and what is true, the strongest invariant, if you want, is P, or after one iteration, by the fixed point, after two iterations, three, the union of all this is the strongest invariant, then I must exit, and that's it. So Mr. Axel move, no, the abstraction, move to this, and then Mr. Axel tell me, you are finished, you have got a proof rules. He doesn't want to go to next. But, okay. So this one is my exercise. You see, I have the definition, few properties of pose. I prove commutation, fixed point abstraction. I get the result. You see. Okay, so now we are missing implication. We have no consequence rule, so we are always speaking of the strongest invariant, and no one wants to do that. So I introduce this order. I have a pair, so X is precondition, Y is postcondition, and I compare the two. And let's go for OR. For OR, I take post of these two orders. And if you say here, if this is a valid OR triple, you under-approximate the precondition, you over-approximate the post-condition, and this is a valid OR triple. You agree? You agree? Oh, okay. You are following at least. So, so under, we said it's a dual. So I take the dual, you see, blah, 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 and I get, this is an incorrectness triple. I take an over-approximation of P prime, an under-approximation of Q, and this is another OR triple. Okay, so now we have done, we apply the Axel correspondence, and you see that we will have a common part between OR and IL, and the only difference will be the consequence rule. Okay? And it's good, but you see, it's sound, it's complete, but it's not really usable because my method given by Axel say, prove the strongest invariant, and then make the approximation. No one does that. But for a mathematician, he's finished, he can retire. It's, so what we miss is fixed point induction. Because we don't handle fixed point or iteration the way I said. You don't look the most precise and then approximate. You just approximate. So the first one for OR will be Park fixed point induction. It's an immediate consequence from Tarski theorem. It says you have a increasing function on a complete lattice. You want to prove that P is over the least fixed point. What you do, you find an inductive invariant, which is more precise. And by Tarski, this implies that, and the other way, the I, you take each fixed point, and it works. Okay, so now for the incorrectness logic, you want to under-approximate the fixed point. Where is this written? Okay, Yes, it's written here. You want to under-approximate, so you take the transfinite iteration, and you go always under the transfinite iteration, and so because you are under some iteration of the transfinite iteration that are under the iteration for the least fixed point, you are in the least fixed point, and this is complete because the x, you just take the iteration of the least fixed point. Okay, so you see that now we have two different things because for OR it's one fixed point induction and for IL it's another one. Okay, so you can calculate, you see I calculate the theory, and here I have applied for OR logic the Park induction, and so I get the rules by, because now it's an axiom, so I get this rule trivially, and I made it, you see, I start from the definition of the theory, I use a fixed point induction, I am happy, and I say, Mr. Axel, tell me that for an axiom it's completely trivial, and because I am not really a serious mathematician, I put the side condition as a precondition, so I mix the rule and the structural induction, but who cares, huh? So I was surprised because I discovered something in OR logic. You see, 47 years later, you discover, it's even more, it's almost 50 years. So what I discovered, if you do pose of equal and less than, you have the same theory, which means the consequence rule, let's go directly to, this rule is useless except for iteration. Because my fixed point induction, I initially P is less than the invariant and so on. And so it was a surprise. Yeah. So now for IL, I take the definition here of the theory, I apply my little theorem, and I get this. So this is a rule of Peter, and to get it, you see, I compute, I use the theorem, it's equality everywhere. Here I have got an axiom, and so I apply Mr. Axel, and that's it. Okay? So simple, huh? So there is more in the paper, because otherwise, if you speak about trivialities, your paper is rejected. And if it's also too complicated, it's also rejected. So there is a balance here, not easy to find, and I almost, I was lucky. So I take a B-inductive relational semantics. It means for finite computation, I use a least fixed point, and for non-termination, I use the greatest one. And some guys say co-induction is better. You have one way of induction for the two, but then you cannot apply my fixed point approximation theorem, and so you are in bad shape. Second, what is the difference? There are more abstraction, so I have more than hundreds logic if you combine all possibilities. Then, so some of them, there is a taxonomy, you can put them. So we have seen these 2 points and this one. Okay, so that's not so bad. The others you can derive yourself. Then I need many fixed point inductions, smaller or greater than the least or fixed point or greatest fixed point. Intersection is not empty, intersection is empty, and things like that. Depending on what you prove, you need many different fixed point induction. And to be serious, I developed in the paper 2 logic. So here is an application. I have factorial, and my logic, I can say if n is positive, f will be factorial. If it's negative, it does not terminate. You cannot prove that with OR logic. This you can prove, but this you have no guarantee of termination. If you take the termination of logic of Mana-Apnueli or Apt-Plotkin or this, you cannot prove this because it's only work if it's totally correct. And then I have another one because Peter, who is there, you see, he promised to ask a difficult question. So I am waiting for the question. So he says, if your analyzer produces an alarm, you can prove it is a false alarm with incorrectness logic. And this is an example where you cannot. So, so I have my factorial. I say n is integer, f is 1, and 47 years ago, I showed how to prove that you know nothing at the end, which was a great result. Huh? But you can specify that it is positive. A factorial is positive. And now it's a false alarm because my analysis will say it can be any value f. So why is it a false alarm? You cannot prove it by incorrectness logic because it is a false alarm because it does not terminate in that case. And so in the concrete, it does not terminate, so it never reaches point with negative. And in the abstract, it can, and this is the origin of the false alarm. Okay, so okay, that's it. And this slide is the last one I gave for Peter, so I repeat it. So incorrectness logic for me naively was incorrect is not correct. So not correct is not or triples. And surprisingly, it is implied by incorrectness logic, but it's not complete. And you must, in fact, invent some R for which it works. And this R is the part of Q which is wrong. There is also a possible part of Q which is correct. So you have to eliminate it and then show that the intersection is not empty. But you see, this formula is not a formula of incorrectness logic. It's some other stuff. And in fact, you can prove it is enough to have one state which is wrong, to be wrong. And if you do that, you can develop the logic, and what you get, a formalization of debugging. So it's very funny. And here is a formalization of debugging, which is interpreted as a logic. And so you see debugging is a formal method. Now. So if you remember nothing of this talk, which I think most of you will do, just remember a transformational logic is an abstract interpretation of a semantics. If this is too hard to remember, just anything is an abstraction of a semantics, and that's okay. Thank you. Okay, so I am waiting for Peter's question. You see, he's ready. He has had 1 week to think about it. I am completely anxious, and so I have to listen carefully.
The title of the paper had you
speak too fast.
You were calculating, in some sense, the title of the paper, the logics.
Yes.
But there's one point that I didn't see the calculation. So you used, I think it was called Park induction for the under-approximate logic, and no, Park was for over, and fixed point induction was for under.
Yeah.
I think you could. I have several questions there. I think you could have used fixed point induction for both. Is that correct?
Both are fixed point induction, but they are different. One is to over approximate, the other is to under approximate. But if you take the dual, then you over approximate and under approximate greatest fixed point.
I know.
And my semantics are not greatest
Correct,
fixed point.
but
And that's why it would not work to have a greatest fixed point semantic, because the abstraction doesn't work.
We agree. This is why the theories are not really dual. But what I'm getting at is that you used, in the over approximate case,
Yes.
I can just choose one loop invariant. And there's various jargons for this. It's like some kind of invariants are complete. Whereas in the under approximate case, I need to have something like a variant function. So I list many of them.
Yes,
right
you have an index invariant.
A proof rule like that is sound in the over approximate case, but we don't need it because of the completeness of inductive invariance. So what I'm wondering is, when you do this calculation, when I was thinking about these, I had to oh, I don't really need that strong induction rule for Hoare, but I need it for the under. So this was all quite puzzling to me. Now, can you calculate that, or do you get similarly puzzled and now you have to invent?
No, at some point you have to have a minimum of intelligence. And that's unfortunate. That is, you cannot push the button and say, give me the logic. You have to say more. You have to say what is the theory, so this is not so difficult. But I think the induction is, which induction you are going to use is difficult. And if you do static analysis, doing the Galois connection abstraction is easy. It's a lot of code. But what is difficult is fixed point induction, which is widening, narrowing, and all these
I have one further question. So the induction rule for the under approximate logic, or the loop rule, looks very much like the loop rules of Pinwelli, the total correctness proof rules. Do they have the same induction principle when viewed from the lens of what you're talking about? They look the same syntactically.
What you said, excuse me. I am dur de la feuille, as we say in France. I don't know is this in English. Dur de la feuille, you know what it means? No. Okay. And the two leaves, in fact. So can you repeat that?
Are the total correctness proof rules and the under approximate proof rules for loops, are they the same induction principles?
They are using the same principle, but you can express it in different ways, and you can introduce, because it's total correctness, you see, you have a property which is more precise than the general case. And then you can introduce well-founded things and so on. So it's a more refined instance of the induction principle. But it's even in correctness logic, I can translate this into a well-founded thing. That is, it must reach under after finitely many steps. That might not be complete, but with hypothesis on the language, it is. So, whereas total correctness forces you infinite steps, infinitely many steps. If you have unbounded determinism, non-determinism here, you might have to go to a transfinite induction. But if it's totally correct, you don't have. So you have a more precise induction principle, but one is the subcase of the other.
My last thing I'd like to say is thank you. And you were wrong in one place. I think many in the audience will remember a lot of things from this talk. So thank you.
Thank you.
All right.
Most questions, so maybe we can stop there. No?
Yes, I think we need to call it off because of
I survived the Peter's question, so I can do it on any other. But I take question if you want afterwards.
Thanks for the patience.